Wait, why is it back? What? This floating panel comes back every 2 seconds.
Oh no. Oh no.
Is it because people are joining?
Oh, because people got, yeah.
Okay. Alex, shit.
Perfect. I think it's 3 p.m. We can get started. Hello, everyone. Welcome to day 2 of the LoG conference 2024. Day 1 was very exciting, a lot of participation, and we hope it increases over the next 3 days.
Okay. Hello? What happened?
Yes. No. Today we have a tutorial, or the first session today is a tutorial on geometric generative models from Joey Bose, Heli Benhamou, and Alex Tong. Hello. Is it working? No? Can you hear?
Yeah, I think you cut off for a second, but we can hear you now.
Yes.
Should we start?
Yes. No, so Joey is a postdoc in Michael Bronstein's group at Oxford, and he did his PhD in Mila. He worked a lot on geometric deep learning and generative models, and has produced some instrumental work in this field. And Alex is Alex is an incoming assistant professor at Duke University, a postdoc currently with Yoshua Bengio, and has also worked a lot on optimal transport and geometric models with single cell biology. Heli is an incoming research assistant at FAIR and currently a final year PhD. The student with Yaron Lipman, and she's also involved in the instrumental flow matching paper. All of our organizers today actually have a lot of experience with workshop organization, participation, and talks. And we hope that they are able to distill all the complex concepts today in a very easy manner, and I'm very much looking forward to the tutorial. You can get started now. Yeah.
Okay, thanks. Thanks for the kind introduction, Vignesh, and thanks for people joining online, and as well as people in the room physically at Oxford. So this tutorial is going to be in 3 parts, and it's about geometric generative models. I'll talk for the first 5 minutes before passing it on to Heli, who's going to take over from there. So before we get started, the first thing I want to talk about is why do we even want to consider generative models, right? So generative models beyond images and text has been a new adaptation of a lot of the cool techniques. So we've seen generative models being applied on domains like proteins, robotics, information geometry, and even climate modeling. So these are all domains that have a lot of rich geometric structure that is not often afforded to you when you try to think of generative models for text and images. And as a result, we need to rebuild tools to tackle these problems from the ground up and also from rigorous first principles. And this is I guess the gateway point for this tutorial, where we kind of build the tools to show you how a lot of the familiar concepts can be elevated to geometric structures, and how do we actually build faithful models on top of these complex geometries. So having said that, this tutorial is going to be essentially three things. One of them is that it's going to be an introduction to main geometric concepts that we actually use to build these models. So we're going to kind of try to distill a lot of the key practices that people are currently using to make more efficient and numerically stable models. And then finally, we're going to try to figure out how to actually code some of these things and see how some of the complex geometric operations actually translate into actual lines of PyTorch code. What this is not is that it's not a crash course on differential geometry. It's not meant to be super rigorous on the math side of things, although we will cover some math concepts. And it's not going to be a rundown list of all of our papers or all the papers in this field and what the state-of-the-art models are, although we will touch upon some design decisions that people use to build these state-of-the-art models. And finally, it's not a history lesson of all prior attempts to tackle geometric data with generative models. It's really tailor-made for what people are currently doing in practice now and the modern generative modeling setup, and how this is kind of elevating the field forward. So having said that, this tutorial is broken down into three parts, roughly an hour each. The first part is going to be by Heli, and the second part is going to be by me, and the third part is going to be by Alex. The first part is going to be a primer on modern generative models, and then we'll move on to geometry as well as the actual bringing the pieces together and how to build these geometric generative models. Wait 1 second. Sorry, this is the wrong slide deck. Yeah, sorry. Sorry, that was the wrong slide deck, but this is the correct slide deck now. So yeah, the first part's going to be by Heli. Second part's going to be by me, which is how do you build geometric tools? And finally, Alex will bring everything together and combining geometry and generative models in practice. So with that, I'll pass it on to Heli. And Heli, please feel free to take over the screen control.
Thank you. Okay, so
How do I go back?
I'm going to share my screen. Do you see the slides okay?
Yes, I believe so.
Great. Okay, so we're going to begin with our first part of the talk about simulation-free generative models. And so let's dive in. So we're going to start by setting the problem that we want to solve in generative modeling. And the setting is as follows. What we have is some unknown data distribution we denote as Q. And we typically have access to it via a finite set of samples, which we denote as X1, and it will become clear later on in the talk why this subscript of 1 appears here. But the setting is that we only have access to a finite set of samples from that unknown distribution. And our goal is to learn a sampler from that unknown distribution Q, meaning that we want to learn some function that is able to efficiently generate novel samples from the unknown data distribution that we're interested in. So this is, in general, the goal of the generative modeling problem. Now, in deep generative modeling, what we do is, of course, we learn a neural network with parameters data. And a generative model could be abstracted into, from my point of view, it could be abstracted into this tuple of two objects. So the first object, psi of theta, is the generator, which is a function that allows generating new samples from the learned data distribution. And P of theta is the underlying density that is defined by this generator function. So for some algorithms of deep generative modeling, we may or may not have access to this underlying density. But in any case, our goal is always the same. We want to find parameters theta such that the underlying density that our generator creates approximates the target density Q. So let's try to put it into a more visual scheme. We have our finite set of samples from the target distribution, Q. And the way that we typically build a generative model is by choosing some easy to sample source distribution, we denote as P, and samples are denoted as Q0. And the generator takes samples from the source distribution and transform them into samples that ideally would be distributed as the target. And as for the modeling of the density, the underlying density, for example, in this case, it would look like this. And if we have access to this quantity, this P of theta, then we would want it to approximate Q. Now, the question is, how do we model psi of theta? How do we model our generator? Because there are so many ways to do that. So in deep generative modeling, we will go quickly about these three paradigms, and then we will continue to the paradigms that we're going to talk about today, which are flow matching and diffusion. But in autoregressive models, we have a likelihood-based model, which sequentially generates the signal that it wants to generate. It is likelihood-based, and the generation is sequential, meaning that the generation depends on the dimension of the signal that we want to generate. This works very well for language modeling, as all of you may know, for LLMs, but it is less trivial of what order to use, for example, for images, or even for geometric applications, where the order of pixels or coordinates of elements in our data is not very clear. The second paradigm of generative modeling, which was pretty much the most dominant one until the appearance of diffusion models, is GANs. And in GANs, the generator is simply a neural network that takes latent vectors from some latent space, which is typically in a lower dimension than the data, and transform them into data samples. Now, training this generator involves defining a discriminator, which receives samples from both the data distribution and generated samples from the generator, and it needs to predict whether they're real or fake. And training this model involves solving a min-max problem, which could be very hard to train. It's a delicate training procedure, and we do not have access to computing the likelihood, which could be interesting for some scientific applications, but it enables fast sampling compared to autoregressive models, for example. And the last paradigm is VAEs, where we define a autoencoder, except now this latent vector is defined to be sampled from some distribution that we restrict while training. So it also enables fast sampling, but we do not have access to likelihood as well. And so far, it has shown inferior performance compared to, for example, GANs. So it has not become such a dominant generative model yet. In this talk, we are going to focus on dynamical systems as generative models. And the way that we're going to view our generative model is by a time-dependent process. So a dynamical system describes the evolution of point samples in time. So now we augment our generator with an extra dimension, and we have a time-dependent generator. And sampling actually becomes simulating. So given a source distribution, we sample a point sample x0, and to generate a sample at time t, and so the choice here for 1 is completely arbitrary, but let's say that at time 1, we want to reach our target, q, and that's why the subscript 1. So we need to learn the components that allow us to simulate this process such that we sample from the target distribution. Now, there are two main dynamical systems that people have worked with to develop generative models. And each of these equations define the instantaneous or the infinitesimal change in that a point sample make in time. So here, the infinitesimal change in x, in the position of x, is dictated by a velocity field that tells us in which direction we need to take this infinitesimal step. And this is this defines an ordinary differential equation. And for diffusion models, we have a stochastic differential equation. So the first part is pretty much the same as the ODE, where now instead of calling this velocity, this is called the drift of the SDE. And the stochastic part comes here. So we have a diffusion coefficient, which is also a deterministic function. And here we consider only diffusion coefficients that depend on time and not on the position x. And a Brownian motion. So the Brownian motion is the stochastic part. And you could imagine that it means that at every time step, you add a little bit of Gaussian noise to your process. So let's see what it means to simulate from these processes. So starting with x naught, we want to solve the initial value problem. And this amounts to basically taking the integral over the velocity. So starting in x naught, we consider trajectory that the point follows, reaching its final point at time t. And for every time on this trajectory, the velocity field, as we already said, points towards the direction in which we need to take our next infinitesimal step. And this is a deterministic function. So if we start from x0 again and we take this integral, we will end up in the same xt. On the contrary, for diffusion, although we write it as an integral, it is not a standard integral because we have here integration over Brownian motion. So this is a stochastic thing. So simulating this process would look something like this. And if we simulate it again, so we start from the same x naught and we take this integration once again, we will not end up in the same position. Okay. So this is something that's important to note. So compared to flows, where we define a deterministic map, here we have a stochastic process or a random variable that is defined by this simulation. Now, these are integrals, but if we are working on a computer, we wouldn't be able to simulate these things. So an important thing to mention is that we have ways to do that by numerically computing these integrals. And there are many standard ways to do that. But I think that the simplest solvers for both ordinary differential equations and stochastic differential equations are the Euler or the Euler-Maruyama methods, which basically say that at each time stamp, if we want to take, we want to move to x of t plus some small delta t, which is the discretization interval of what we integrate over. So we take a step in the velocity direction times the time interval, the discretization interval. So and for diffusion, it's similar, except now we have this, again, the Brownian motion term here. Okay. But we want to build a generative model out of this. So the question is, where are the probabilities, right? I mean, when we build a generative model, we want to be able to make the probability density of our model match some target. And in fact, both these dynamical systems have characterization of how either the velocity field or the drift and the diffusion coefficient are tied to the evolution of the probability density in time. So if we start with samples from a source distribution P, and we simulate their trajectories according to the velocity or according to the SDE that is defined by the drift and the diffusion coefficient, then we know how the probability densities will change in time. And this is a major thing. And in fact, we can kind of say that for flows, if we have UT, if we have the velocity, so maybe we can build a generative model out of this, right? So we can have UT and make it evolve to a probability density of our desire. And on the same note, for diffusion. So can we build a generative model with this? And the answer for flows is quite immediately yes. But for diffusion, we need one more thing. And we're going to go over it now. So in diffusion, the stochastic differential equation actually only describes the forward direction. Okay, so if we start from from the data distribution, simulating this equation, simulating this SDE would only add more and more and more and more noise, eventually at infinite time, reaching a stationary distribution of this stochastic process. Now, if we want to build a generative model, we need to be able to simulate the reverse one, right? We want to start from a noise sample and then transform it into a data sample. And to do that, there is a reverse process that has the same marginal distributions, meaning that P of t, the distribution at time t, would be the same for both the forward and the reverse, but it depends on where we start to simulate it. And the reverse SDE is formulated with the one more thing that we need, and it is the score function, which is the gradient of the log density at time t. Now, for learning a score-based model, it has been shown in diffusion and score literature that we can learn the marginal score, by regressing to conditional scores. And I intentionally write here P data and not Q because the times in diffusion and in flows are reversed. So we're clear that here we're taking a sample from the data. X is a data sample, and we simulate the forward process, and that yields the conditional flow on a data sample. And why we call these models simulation free is that for certain SDEs, we have ways to first actually sample from this conditional distribution without having to simulate the forward SDE. They have closed form expressions. And the second thing is that we don't have to simulate the process at all or backpropagate through it during training this model. And we're gonna be using these similar principles when we build a flow matching model, so keep that in mind. Okay, so to build a diffusion model, what we need is to learn the score. And a few things to note here is that we could only use it with a Gaussian source distribution. This is kind of a limitation of diffusion models that is going to be lifted when we use flows. And we'll also discuss why it is beneficial to use flows over diffusion for geometric applications. And also the solution only reaches the source distribution asymptotically. So we have to simulate our process for a very long time, ideally to infinity. So, and this incurs errors when we want to simulate the reverse process because we do not really reach the source distribution. Now, we move on to flows. So when flows, things are actually a bit simpler because under some very reasonable regularity assumptions on the velocity field, it will define a flow psi of t. And this flow function defines a diffeomorphism on the space, which means that it is smooth and it has a smooth inverse. And this inverse is defined by simply minus the velocity field. So compared to diffusion models where simulating forward in time and simulating backward in time involve different components and different objects that we need, here all we need is the velocity field. Which makes things a little bit simpler when we want to build a generative model with these. So to build a generative model with flows, what we need is to learn the velocity field. And in fact, it can define a universal transformation between densities. What it means is that we can start off from any source distribution to any target distribution, and we are guaranteed that there exists some velocity field that transfers between these two. And this is compared to the limitation of a Gaussian source for diffusions. And the second thing is that it is defined on a finite time interval. And again, we don't have these errors in the boundary of small mismatch between our distributions. So we're now going to deep dive into building a flow matching model. We're gonna revisit diffusion once in a while, but the main focus of the talk is going to be on flow models. So we said that we have the flow ODE that describes the motion of point samples in time, and correspondingly, we have the continuity equation, which couples between the velocity and the evolution of the probability density in time, and we can see it visualized here in these nice GIFs. And now the goal when we want to build a flow generative model is to find a velocity field UT such that the terminal distribution P of 1 would match our target. Okay, so we refined a little bit our goal for a generative modeling problem for the flow case. So using flows as generative models were originally introduced in the neural ODE paper by Chen et al. And what they suggested was to use the fact that we can compute the log likelihood of the model. Okay, so a little algebraic massage to the continuity equation would give us the equation here on the right. And this basically means that if we can compute the log density of our source distribution, which is true if we chose it to be a Gaussian, then we can integrate over the divergence of the velocity field to get the log density of the model at every desired time. And if we can compute the log likelihood of our model, then why not use the maximum likelihood objective to train it? Sounds like a good idea. However, it requires a lot of computational overhead. Why is that? So first, we need to simulate XT during training, right? Because we need to evaluate our velocity field at every XT. And furthermore, we need to take derivatives of our velocity field, which we don't have a very efficient way to compute the divergence in high dimensions. So we resort to some, although unbiased, but to an estimator. But the main thing is that we also have to backpropagate for this simulation. So this becomes very heavily computationally to even train such models, and flows have not been scaled up much until the introduction of flow matching like types of models. So here we are. So basically, flow matching was introduced in the same time with stochastic interpolants and rectified flows. They were all published in the same ICLR conference in 2023. And although they arrived in the same method eventually, they did come from a little bit different perspectives. And we're going to follow the flow matching perspective on building a simulation-free method for training flows. Okay. So the basic idea in flow matching says, okay, so we said that we have the continuity equation that couples between the velocity and the distribution in time. And the core principle that we're going to follow in suggesting our training objective is the fact that the velocity field generates a probability path if and only if it satisfies the continuity equation. So that means that if we could build some probability path that starts from a source distribution and reaches an approximation of our target distribution, then we could regress to the velocity field. And if we have the velocity field, then we have a way to generate samples from that distribution. But to do that, we need to do two things. So the first thing is we have to build this target probability path, and it needs to satisfy the boundary conditions, starting at the source and at the end, reaching an approximation of the target. And we need to have the generating velocity field UT. The second thing that we need is to find a tractable optimization objective for this, because at this point, a few of you may wonder, okay, but if you have your velocity field in hand, why do you need to learn it, right? So we're not going to have it in hand. We're going to find some other way to do that, and that's going to be involved in finding the tractable optimization objective. So we're going to start with building our target probability paths, and that's going to guide us towards finding our tractable objective as well. So to build a conditional, we build a probability path by building conditional probability paths. So our boundary conditions are, as we said before, and we use the law of total probability to define our probability path as a marginalization over some conditional probabilities. Where if we choose our probability path, for example, to satisfy that at time 0, it is simply the source distribution, and at time 1, it takes all of the samples to the x1 sample from the data that it is conditioned on. And if we plug in these two into this integral, we will easily see that it satisfies the boundary conditions. So just for notation, and so we understand what we say. So this is called the marginal path, and the conditional path is called the conditional path. And now we're going to see how we're going to build the velocity field that generates it. So for the conditional path, there exists some conditional velocity field that generates it. And we can express the marginal velocity field that generates our marginal probability path in terms of the conditional velocity field. Okay, so we turn our problem of finding the marginal to the marginal velocity field into marginalizing over some conditional velocity field that is potentially easy to compute or find. Okay, so looking at this ugly integral, we are not done yet. We do need to further find a tractable objective. But I want to note that here we could also marginalize over any condition, and some useful different conditioning that could be used is to, instead of conditioning over only the x1 only over the data points, we could condition on both a source sample and a target sample. And this will open up the option to define different kinds of couplings between the source and the target. You could look into these two papers below that, for example, suggested solving mini-batch optimal transport couplings between the source and the target to make the learned trajectories straighter, and hence to have faster inference when solving, when simulating from such flows. And another option is to condition on x naught, which will, as we will see later, connects to the epsilon prediction or noise prediction in diffusion models. And just for notational simplicity, by Bayes' rule, we could switch all this to just reverse the conditioning. So here we have PT of z given x, so it's like simpler to write it down. Now, we need to find our conditional flow matching loss that will allow us to actually train such a model. So similar to in score matching, as we said that we could regress to a conditional score to learn our marginal score, it turns out that also for flow matching, we have this equivalence. So the minimizer of the flow matching loss is the same minimizer as the conditional flow matching loss. And actually, only by building conditional velocities, we could learn the marginal one that generates our PT, our desired PT. So we're almost done. Okay, so we built our target probability path, and we defined the velocity field that we want to match, and we found a tractable objective. But the last bit that we're missing is how do we compute the conditional velocity for some conditional probability paths. And the way that we do it, and that is pretty, I think, relatively easy to construct, is to build these conditional paths by building the conditional flows. All right, so the conditional flow simply tells us if we take a point sample at time 0, where it will end up at time t, and the derivative of the flow is the velocity field, right? It's connected by the flow ODE. So we will build the conditional flows such that at time 0 they leave the point in place, and at time 1 they take all the points to the conditioned sample x1. Okay, so we have the conditional probability path, the corresponding velocity field that generates it, and the corresponding flow that is defined by this velocity field. Okay. Now, a popular instance of conditional flows that are used are affine conditional flows. And they simply, they're called affine because they're an affine combination of x1 and x0, where alpha t and sigma t are time-dependent coefficients. And in order to satisfy the boundary conditions, we would need alpha t to be 0 at time 1, and sigma t to be 1 at time 0, and sigma t to be 1 at time 0, and vice versa. Okay. Now, to get the velocity field, we write down the flow ODE. Okay, so we have the time derivative of the flow is equal to the velocity field evaluated at the point flowed with psi, condition on x1. And computing this derivative, we get that it's simply the derivative of alpha t with respect to time x1 plus sigma t dot denotes derivative with respect to time times x0. And if we plug in, like we take x0 out and we plug in that so that we can evaluate the velocity field for every position in space and not just on trajectories of the flow, then we end up with this expression. And in fact, we could have various prediction types that are related to flow matching. So if we condition our velocity field on x1, and then we marginalize. Okay, so we take the conditional velocity field, here z is x1, and we marginalize to get the marginal velocity field. We will end up with a velocity field that is a function of x and of what people typically call x prediction or denoiser. And we can see that we can transform from the x prediction to the velocity field in a very simple affine functions. The same goes for epsilon prediction. So if we condition on x naught and marginalize, we will have the expression that connects between the velocity field and epsilon prediction. And lastly, if we condition on both, we'll have an expression that's dependent on both. So in fact, we have shown that all of these types of predictions are transferable, and we can move from one to another quite easily. One instance of a choice of conditional flows that are used and was proposed in the flow matching paper is to use affine conditionals that connect x0 and xt in a straight line. So it basically is a linear function. So alpha t is t and sigma t is 1 minus t, and we connect between them in a straight line. And the corresponding velocity field would be x1 minus x0. Okay. We could also instantiate flow matching for a choice of a Gaussian source distribution, of course. And in that case, x of t will be distributed as a Gaussian. And we could also instantiate both the variance exploding and the variance preserving schedulers that are popularly used in diffusion models. So we see that we have lost nothing in terms of the expressiveness of our model when we move to flows. So we could also create these paths with flow models. But on the other hand, we cannot create, for example, the conditional optimal transport paths with diffusion. And just to visualize how these trajectories differ, these are conditional trajectories. So the black points are initial sampled from x0, and we see how the conditional flow moves them to x1, which is the red point. So with condo T, we see that these are straight lines, and with variance preserving, we see that the trajectories sometimes overshoot the sample and like go above it. Okay, so we have defined a way to build our generative model. And let's put it into some recipe that we could follow. So given a set of samples from a target distribution Q, we need to construct a probability path, PT, such that at time 0, it is the source distribution, and at time 1, it will reach an approximation of our target. And the way that we build these probability paths is by building conditional flows. And to learn our generative model, we need to learn a velocity field UT with the conditional flow matching loss regressing to conditional velocities, where our goal is to build marginal flows that generate PT. Okay, so now we're going to have a short coding session trying to put these things into so one sec. Okay, so do you see my screen?
Yes.
All right. Okay. So we're gonna build a very simple example of a flow matching model on a two-dimensional data set, and we're gonna follow our recipe for building this model. So we're gonna have our data and then construct the probability path by defining a conditional flow, and then we're gonna write down the training loop, and eventually we're also gonna sample from it. So I have pre-cloned the repo, and we're gonna need it for our data set. And here we have defined the architecture. So these are standard setup for neural network training. We're not gonna go over it. So we define our architecture, which is a simple MLP. And then we define the model that will represent the velocity field that we're learning and the optimizer that we're gonna use. And now let's define our data. So in the assets directory, we have two images. One is like an image that says log, and the second one is one that says 2024. And we're gonna create 2D distributions based on a mask, on these masks. So here we have a function that samples uniformly from the white digits or letters. And so let's sample from our data. Oh, what happened? I'm not in the right directory. Oh, okay. Oh, yeah, I'm not sure where I am. Okay, I'll just use absolute paths so we don't waste much time on this. I don't know what happened. I switched them. Okay, something is wrong here, and I'm not sure what it is. Okay, so let's try the other way around. We'll try to connect to a hosted runtime. Sorry. There aren't any GPUs. Okay. Do you have any questions in the meantime while I try to solve this problem? Okay, so we're gonna try this. Something is wrong. Maybe it's this thing. Okay, Joy, do you wanna maybe go ahead and continue and we'll try to get back to it later?
Yeah, so I can take over the second part, but for what it's worth, some of the people in the audience say that it's working for them, so I think it's maybe stochastic.
No, I mean, I don't know what, like, I mean, you see that, like, the images exist in the path, and I opened them.
That's totally fine.
So
So
another thing we could do is, I mean, we could just maybe go over this. I'm sorry for, I don't know why it doesn't work. But maybe let's go real quick over this. So if you sample from these masks that I showed you, you will get these source samples, which write out log, and the target samples are going to write out the 2024, and we're going to try to learn a flow model from log to the 2024 distribution. Okay, and now, so this is the data, and now we're going to define our conditional flows. So for conditional optimal transport, we have a very simple expression for our flow. So x of t will be 1 minus t times x0 plus t times x1. And the velocity field is the time derivative with respect to time, yielding x1 minus x0. So to write down the training loop, so we need to take our expectations over time uniformly. And we need to sample points from our source and our target distribution. So this is the function that samples uniformly from the mask. We're going to compute our conditional flow, x of t, and the conditional velocity field, ut, and run out the model to compute the neural network prediction of the velocity field. And our loss is simply an L2 distance between the predicted velocity field and the target conditional velocity field. So if we train this for a while, and in the meantime, we were supposed to write down our Euler solver that will allow us to simulate from our model. So Euler solver, as we presented in the slides, it gives us a recursive formula for evolving xt in time. So xt in the next step would be equal to xt plus the velocity field times the discretization interval that we chose. And this discretization interval is defined by the difference between the end point in time and the start point in time divided by the number of steps that we want to take. And we also need to progress t as we take our steps. Now, if everything works and we take our model and we sample from our Euler sampler, we can see that we generated samples that write out 2024. And eventually we could animate the point trajectories. So this should work, I think, because it's independent. So here we see the flow of like going from the source distribution of writing out log to the target distribution 2024. So I think it's a nice illustration of the flexibility of flow matching that we can use any source, any target distribution, and learn a flow model from that. Okay, so that was less successful than expected, but let's move on. I have like 2 more slides and we're done. Okay, So you can see my screen. Oh, it's the other screen. Okay. So flow matching has been extended to very various interesting applications. The one that we're going to be focusing also in the next parts are flow matching for general geometries. It has also been used for designing equivariant models for two permutations and all sorts of symmetries. I think the most prominent use of flow matching is the adoption of the stable diffusion 3 model to use flow matching instead of diffusion models. It has also been used for control generation and to solve inverse problems, also utilizing the fact that we could use any source distribution that we want, so to learn different types of generative models. So to sum up this part, we've shown that flows are powerful generative models when they're supervised adequately, for example, with flow matching. And it gives us a flexible framework for training generative flows. And compared to diffusion, they also incur improved sampling speed and stability when we use the conditional optimal transport paths compared to the variance preserving, for example. So now I think that some open challenges on this part is that we still have to simulate the process. So sampling a point from the generative model does involve taking multiple forward passes through the neural network, which could be prohibitive. So it's still a challenge to learn a one-step model that performs as well as these models without distillation. And the second thing is to scale these to other domains, because I mean, flow matching has been very successful for images, but for example, on language, it still does not match the performance of autoregressive models. So on that note, thank you for listening, and Joey, you can take over.
Thanks, Helly, for the great first part of the tutorial. Let me start sharing my screen and then, oops. Yeah. Let's go here. So in the meantime, maybe if there's any questions, we can take some questions now. Otherwise, we can jump straight to the second part of the tutorial, which is going to be how do we build in geometry for machine learning? Okay. If there's no questions, I'll get straight to the point and get started. So when we think of generative models on manifolds, the first question you have to ask yourself, like, which of the current things actually remain constant and which of the current things need to be rethought from the first principles? So for instance, our data previously was on a regular Euclidean space. Now, the first choice we have to think about is like, well, what happens to the data when you parameterize on a manifold? And how do we construct probability paths? Before, they were quite simple. There were straight lines. But on manifolds, there's no such easy notion of straight lines, or the conventional notions have to be adapted. And how do you build conditional flows? And even how do we define velocity fields? And all of these things need to be kind of elevated to manifolds. So this brings in many questions. The first question being, how do you even represent a point on a manifold? This is a design decision. Also, in regular flow matching, we had kind of a Gaussian source distribution, or even in diffusion. Unfortunately, for manifolds, there's no canonical definition of a Gaussian distribution. There are obviously analogs to it. So the choice of a source distribution has to be adapted as well. So there's different choices, and it's unclear which is always the superior choice. And more importantly, when you define your flow map, regular Euclidean flows, we could easily do alpha t times x1 plus sigma x0. Unfortunately, manifolds don't have this vector space structure, so we can't do addition. So this immediately breaks. So this has to be elevated. So even defining straight flows is a challenge. And lastly, the notion of velocity and vector fields also need to be kind of generalized to manifolds. So we're going to tackle these points, but in doing so, we're going to try to think about it from the point of geometry. So what do we need to invoke in geometry to enable us to define these concepts for generative models? The first thing is that, well, how do we even characterize points on the manifold? So your data distribution that we want to represent. Well, to do that, we can think of it, we have to first define what a manifold is. So for the purposes of this presentation, and this is not going to be extremely rigorous, but it's going to be serviceable, you can think of a manifold as being a smooth topological space that locally looks like a vector space, but globally, when you glue together these patches, looks totally different. As a result, we can say that each point belongs to this topological space. But even when you do this, you have to think about certain considerations. So when you're doing generative models, how does the curvature of the manifold affect numerical stability? How do we even parameterize this manifold? There's more than one choice. Do we use extrinsic coordinates? Do we use intrinsic coordinates? And other choices. And finally, what additional structure do you need to impose to actually do generative modeling? So just having a topological space is not enough. Even though it's smooth, it's not enough. We need to add additional structure, and we'll see the structure that we really need is the notion of a metric, which allows us to define distances as well as angles and norms. So moving forward, so let's be a bit more formal about what a manifold is. So a manifold, as I mentioned earlier, there's local patches that kind of look like Euclidean spaces. So more formally, these things are called charts. So each chart is an open subset UI, and it has a corresponding homeomorphism phi that takes you from this chart to a corresponding Euclidean space. So in this picture over here, we have some manifold, and we're covering it with these subsets, and these subsets may intersect at different points. And from each subset, there's a chart, there's a map phi that takes you to an equivalent Euclidean space. And the reason this is cool is because, well, we know how to do deep learning and generative models in Euclidean space. So we want to be able to use this fact or exploit this fact to kind of do generative modeling on manifolds. So the one thing we have to note is that when you define charts that cover the manifold, we have to first assume that the charts are smooth. So we've already added some structure to the problem. Smoothness means that the charts are, and the maps between charts are going to be C infinity, so infinitely continuous and differentiable. And this is an important criteria because the vector fields that we will define have to satisfy this property. So in this picture over here, if I define a subset U, I want a chart that takes me to a corresponding space that's mapped under the chart. And then correspondingly, if there's another chart Uj, there's a corresponding homeomorphism phi j that takes me to a corresponding Euclidean space. Now, the key condition that holds everything together is how do we glue charts together? So more specifically, if the charts intersect at certain points, we need to be able to handle this criteria, this area over here. So this chart-to-chart gluing is a technique where you can kind of just follow the arrows. So you go from phi, and then you go from phi j to phi I inverse, and you can go back to uj. So there's an easy compatibility condition that needs to be satisfied, which is to say that whenever charts intersect, there's a smooth way of going from chart to chart. And as a result, you can kind of glue together a manifold by just picking different charts such that they cover the entire manifold. And each chart has its own, you can think of it as its own phi map, which allows you to define a corresponding local Euclidean space. And that's kind of the high-level idea. So having said that, how do we actually represent a manifold? So there's more than one way of representing the same geometric object. The two main ways I'll talk about is extrinsic versus intrinsic. So what do I mean by extrinsic? So extrinsic means you take a manifold and you embed it in a higher dimensional Euclidean space. So in the picture over here, we have a sphere in R3, so R3 being the ambient space, and the sphere is S2. And we can say that the sphere lives or is embedded in this higher dimensional Euclidean space. And the way you do that is that more formally, you can embed any manifold by defining what's called an inclusion map. So the inclusion map is this function iota that takes every point on the manifold and sends it to an equivalent point on Rn. And the general principle is that we want to kind of, when you think about parameterizations of manifolds for generative modeling, we want to think like a deep learner, which is to say that let's make it as close as possible to something that already works, and we know is scalable, and we know how to work really well with Euclidean spaces. So extrinsic parameterizations of manifolds are very nice for this exact reason, because you can use the coordinate system of the ambient space to do a lot of your deep learning machinery. So one quick advantage over here is that the ambient space is a vector space. So a lot of the familiar operations like addition are permissible in the ambient space, which may not be permissible on like a regular manifold. So that's something to think about. So another equivalent choice is an intrinsic coordinate system. So when I say intrinsic, I mean a local coordinate system where you just choose charts. and the charts that cover the manifold. And you do all of your computation in these charts. So a very simple example for the sphere, because the sphere is such an illustrative example, is that you can do something called stereographic projection, and you can cover the sphere with two charts. And these charts are essentially divide the North Pole and the South Pole. So if you take a point on the upper hemisphere of the sphere, and you start drawing a line from that point and see where it intersects the plane that cuts the sphere in half, that's called the stereographic projection of the sphere. And you need two of these charts, so U plus and U negative, to cover the top half of the sphere and the negative half of the sphere. So immediately, there's a problem with this parameterization, not from a mathematical point of view, but from a machine learning point of view. The problem is that you slowly reach numerical instability as you get to the poles. So when you're thinking about doing generative modeling using these charts, you have to be conscious of this fact, because for normal geometric applications, when we actually do numerical computation, this could be a problem. So as a result, one preferred solution is to maybe perhaps use the extrinsic coordinate system as opposed to the intrinsic coordinate system on the sphere. So another equally valid choice of coordinate system for the sphere is that you can use what's called almost global coordinate system. So any point on the sphere can be represented by some radius from the origin and some angle theta and some angle phi. If you give me these three things, I can pick any point on the sphere and represent it as a valid parameterization of a point on the sphere. So many times this is going to be also a favorable parameterization. So again, one thing you have to consider is that just when you pick a parameterization, what is the actual potential drawbacks, right? One drawback is that because we're using angles, we have to use trigonometric functions. And can these trigonometric functions be always numerically stable? And also their inverses. So sometimes when you do computations, you have to compute inverses of these trigonometric functions. And as a result, for small angles, they could be numerically unstable. Okay, so the next object that we really need to define is that for diffusion models and flow matching models, everything is related to defining velocity fields and vector fields. So to generalize the notion of velocity and vector fields, we need to define a tangent vector. So a tangent vector is essentially for every point P on a manifold, you define a function that takes you to Rn. And we want to kind of essentially say, oh, a tangent vector is tangent to a point on the manifold. So in this picture over here, we have the point P. And a tangent vector is, you can think of it as like living on the tangent plane attached to the point P. Now, we'll have a more formal definition, but the picture is essentially the same for all types of manifold. You want to define a tangent vector that's essentially tangent to some sort of curve at a particular point. And if you have a local coordinate system, we can always represent the tangent vector using the local basis. So in this picture over here, imagine your tangent space, which is the set of all possible tangent vectors at a point P. You have a basis vector, so you can represent each tangent vector at this point using the equivalent tangent basis. And this is what we call a local basis to represent the tangent vector. So a bit more about tangent spaces. So a bit more formally, a tangent space, you can define it as like, by first defining a parametric curve, which is time dependent. So if you pick a curve gamma that goes from, let's say, -1 to 1, such that it passes through the point P at gamma equals 0, you can think of a tangent vector being the time derivative at that point on the curve. And as a result, you can think of this as the ddt of the curve gamma evaluated at t equals 0. So that's formally what a tangent vector is. It's literally a tangent to an equivalent curve that's passing through that point. Now, as a result of this, because we have the tangent vector and we have a local chart at that point, we can always say, oh, we can take the basis vectors and RD and pull them back by using the map phi inverse to define an equivalent set of basis vectors for the tangent space. So this gives you a local parameterization for how to define a tangent vector using intrinsic coordinates. So a bit more formally, if you have a point P, you can say the local coordinates of the point P is essentially given to you by a differential. So let's say d phi P, which pushes forward tangent vectors from the tangent space at point P to equivalent space RD, and you pull it back by taking phi inverse. So each tangent vector in the basis of the tangent space can be represented by pulling back through phi inverse the equivalent RD vectors. And that gives you a tangent basis. So as a result, we can take the vector v in the tangent space and rewrite it using the coordinate system of the tangent space. Right. So I told you how to define tangent vectors using the local coordinate system, but I also said that extrinsic parameterizations of the manifold may be favorable for some computation. So the natural question is that can we exploit this extrinsic parameterization to define tangent vectors in the ambient space? And the answer is yes. And the way we do that is to say that, oh, you can always embed your manifold in a higher dimensional ambient space. And because we did it through this inclusion map, which tells you for every point, there's a corresponding point in the ambient space, we can also pull back the coordinate system of the ambient space back, from the manifold back into the ambient space. And the way we do that is to say that, oh, we'll take the phi inverse map, which is from the chart, and then we compose it with Yoda. And as a result, we take the local basis vectors EI, and we just add it the Yoda and phi inverse composition, and we have an equivalent way of representing tangent vectors, but with the coordinate system of the ambient space. So this is super powerful and super cool because you can kind of essentially do all of your computation in the ambient space using the basis vectors of the ambient space. So this gives you a natural question, which is, how should we parameterize your velocity fields, right? So our velocity fields is kind of what we care about when we're doing flow matching, and equivalently for diffusion. How should we parameterize them? So one direct option is to say, well, output directly to the local chart, so that we'll say the output of our network will be directly on the tangent space at a point P. Or alternatively, we can output them directly in extrinsic basis, but the extrinsic basis, because they're built from the tangent basis, they will automatically be on the tangent space correctly. Or finally, we can kind of take a velocity field in the ambient space and project it to the tangent space if you have a projection matrix P. So in pictures, this looks like this. So we have our local parameterization, and then our extrinsic parameterization, where we have to change the basis vectors using the basis vectors of the ambient space. Or alternatively, we output essentially in the ambient space without caring where the manifold is, as long as we have a projection matrix to project it back to the tangent space at a point P. So for certain manifolds like the sphere, we often have this in closed form. But for many manifolds, this could be too difficult to compute, too expensive, or not available in closed form. And as a result, it really depends on which type of manifolds you're working with when determining which method you want to use in practice. So for the sphere, this is really easy to compute. But for another manifold, we may not have this. So now that we've kind of talked about tangent spaces as well as smooth manifolds, what other structure do we need to actually invoke or kind of build flow matching and diffusion models? So the first thing is to realize when we're trying to build flow matching, the loss function required us to compare vector fields, or velocity fields rather. And in this example over here, we use the 2 norm. But the problem is in manifolds, we don't have an equivalent version of the norm yet. So we don't know how to compute this quantity. So we need to invoke additional structure to enable us to compute this quantity. And more importantly, we don't even know how to compute xt. So xt is this point along the straight line path we had in Euclidean space, which is telling us the particle that's moving from time 0 to time 1. So the main structure that we need to add is this notion of a Riemannian metric. And this metric is going to be super useful to us because it allows us to actually define an equivalent norm on the manifold, as well as define distances and other useful properties. So more formally, a Riemannian metric is a selection or an assignment of inner products that varies smoothly on the tangent space. So this inner product consumes 2 tangent vectors, and it's defined at a particular point P, and it varies smoothly at every point on the manifold. And this is a very important geometric structure because for spheres, the way you define the sphere is to say that every inner product for 2 tangent vectors gives you a positively curved quantity. So 1 over k is essentially the curvature constant of a sphere. And it's a constant curvature manifold because no matter where you are on the sphere, the metric is the same. So I just want to reiterate one more time that choosing our metric is a choice. So we've decided to add this choice because we wanted to be able to compute this loss function over here. And if we were trying to do other geometric deep learning operations, maybe we don't need to make this choice. And more importantly, you can equip a different metric for a different space, and it's a choice based on the modeler. So we could have picked a different Riemannian metric on a space, and then we would have had a different modeling problem. And sometimes you choose a metric based on convenience rather than a prescription. So having chosen a metric, a Riemannian manifold is formally a space, a smooth manifold M, equipped with a metric G. And this metric G is defined everywhere on the manifold. So common examples of Riemannian manifolds are, of course, the Euclidean space. Then the metric of the Euclidean space is just 1. The sphere, where the metric is 1 over k at every point. And hyperbolic spaces, which is the foil to a sphere, where the metric is negative 1 over k. So here's an example of a hyperbolic space. So over here is the hyperboloid model of hyperbolic geometry. There's more than one model of hyperbolic geometry. But you can see that this space is negatively curved rather than positively curved, which is the sphere. So why are metrics kind of important? So Riemannian metric is important because, as I will explain to you in a second, they enable us to compute a lot of important quantities. So we can compute lengths of vectors, which is the norm. We can compute distances, and we can compute angle. And again, the metric, it consumes 2 vectors on the tangent space, so UV. And to actually use this in practice, it's just U transpose G, where G is the matrix representation of the Riemannian metric. So G is a positive definite matrix, and it's going to be different for each point on the tangent space, or each point on the manifold, rather. So how do we actually use a metric to define norms? So the way we define a norm formally is a square root of the inner product between the same vector twice. So U inner product square root is formally the norm of a vector, and it measures the length of the vector. Similarly, you can define angles as follows. You can say cos theta, when you're in a tangent space, is the inner product of 2 tangent vectors UV divided by their norm. And once you have this norm, we can now actually define the loss function for flow matching a bit more crisply, because what changes between the top one and the bottom one is this addition of this metric. And now the norm is computed with respect to the metric. So now we can actually compare and compute this loss, or the norm for this loss, rather. Now, so the last thing we need to introduce is that, well, how do you measure distances on a manifold? So distances, the way you do that is if you pick 2 points between the manifold, so let's say points P and Q, we want to find a curve gamma that passes through P and Q, and is the shortest path between P and Q. And the curve gamma that is the shortest path between P and Q is called the geodesic, and it's also the straightest path in the manifold sense. So the main idea to actually construct the distance is to say that, oh, we'll pick a curve, or we'll take a parametric curve, and we'll measure the length of the vector as we traverse the curve. So we'll measure the norm from times 0 to 1 as we compute the tangent vector to this curve as we traverse from P to Q. And the idea is that this, because we have a metric, we can measure the norm or the length of the vector as we traverse the entire parametric curve. And the distance on the manifold is defined as the curve that minimizes this integral. So it's a very natural definition of a distance. So a couple of facts about this distance is that it is actually the shortest path, like I mentioned, and the shortest path is called a geodesic. It is also the straightest path in the sense that it is the straightest with respect to the metric. And because it's the straightest path, it's also the most kinetically optimal path. So traversing this path will give you the lowest kinetic energy. And if you pick any other curve between P and Q, you will necessarily incur a higher kinetic energy, or more energy needs to be used to traverse this path. So sometimes it's a bit confusing to think about geodesics, but it's really easy when you actually visualize them. So over here, what I have is a visualization of the probability simplex. So the probability simplex is essentially, you have a manifold where each point is a categorical distribution inside of the interior of the simplex. And I want to essentially draw a path between this blue dot and this orange dot. And each point along this path is going to be another categorical distribution. So if I draw a linear path, you can see the line is straight. But if I change the metric on the space to another metric, which is called the Fisher-Rao metric, you can see the path essentially bends. And this is the bend path is now the shortest path with respect to a different metric. And this metric allows you to kind of bend these paths. And the main thing I want to highlight here is that different metrics induce different geodesics. So you can have the same space, but by choosing a different metric, you've changed the geometry of the problem. So the Riemannian metric is really a very important gadget. Okay, so because we picked the Riemannian metric, we can compute distances, we can compute angles, we can compute norms. What does that actually allow us to do? So if you recall, in the flow matching equation, we had to compute this loss function, which is the L2 regression of the target velocity field with the one that you're learning. Also, because we can compute distances, we can now compute an equivalence between these two objectives, which is to say that we can use the X1 prediction or target prediction framework and say that we would just want to minimize the distance between the predicted endpoint and the actual ground truth endpoint. So this is a completely equivalent loss function to the first one, except that it uses a different parameterization. So your network over here would predict the endpoint rather than the velocity at an intermediate step. Similarly, for diffusion, we wanted to predict kind of the score function, and we want to regress to the score function. So we can do that now because we have essentially the same norm. And as a result, we can also compute the equivalent of target prediction for diffusion models, which is called epsilon prediction. We want to predict the noise added to your sample. And I remind you, all of this is connected in the Euclidean setting with an ODE and an SDE. However, one thing that's still not clear to us so far is how do we actually integrate on the manifold? Because we don't know how to simulate this ODE in Euclidean spaces. And the reason we don't know how to simulate it is because, again, the manifold by itself doesn't have a vector space structure. So we don't know how to do an Euler step yet, or Euler-Maruyama step for SDEs. So to make this a bit more crisp, when you simulate flows in diffusion models, in Euclidean settings, the actual Euler integration is telling you, oh, the t+1 step is xt plus the velocity prediction times some time delta. So we just move along this path for time delta t, and we get to the next point xt+1. Similarly, for diffusion models, we have a similar prediction where you move along this direction, which is controlled by your score function, plus you add a little bit of Brownian motion, and then you just keep going along this path. Now, what breaks for manifold? And you need the next point to be guaranteed to be on the manifold, because if you just arbitrarily add two things, you will not be on the manifold. And finally, for the SDE use case, the hard thing is, how do you define Brownian motion on a manifold? Because at the very beginning of this, I told you there is no canonical definition of a Gaussian distribution. And even though there's always a way to define Brownian motion, it may not be easy to compute in closed form. And for many manifolds of interest, this is actually a very tricky object to compute. All right, so to compute the actual Euler integration, or the equivalent of integration, we need to introduce a couple more manifold operations. So the first thing we have to introduce is, like, how do we move from a point on the manifold back to a tangent space? And how do we move from the manifold to a tangent space and vice versa? And finally, how do you move vectors between tangent spaces? So the first operation is the exponential map. We'll take a vector and find the corresponding vector on the manifold, corresponding point on the manifold. And the logarithmic map is the inverse of the exponential map, where you take a point on the manifold and you bring it back to an equivalent tangent space. And finally, the last operation is called parallel transport, which tells you if you move a vector from one tangent space to another, what is the curve that has to follow so that you don't change the vector in some sense. So the first operation, as I mentioned, is the exponential map, which tells you if you give me a tangent vector at a point P, how do I find the corresponding point on the manifold if I do an operation? So in pictures, the exponential map is very simple. It says that, oh, if I start at a point P and my instantaneous velocity is V, and if I find the curve gamma that corresponds to this velocity vector, where will this curve take me if I follow this curve for time 1? So if I follow this curve in the direction of V for time 1, where's the point on the manifold that I will land? And the output of the exponential map as a result of this is a point on the manifold. And we travel a unit of time along this curve gamma. And conceptually, this is kind of similar to addition in Euclidean space. So for spherical geometry, the closed form expression of one exponential map is this nasty looking term over here. So already you can see that computing this is a bit more complicated and involved compared to just adding in Euclidean spaces. And this operation will, of course, change depending on which manifold you're in. Now, the inverse of the exponential map for most cases is logarithmic map. And the logarithmic map is exactly the same idea, but in reverse. Yeah. So there's a question in the audience. Yes.
That operation underneath for all the fields
It can be expensive, yes. Oh, sorry. Let me go back.
Joey, can you also repeat the question?
Yes, of
Yes.
course. Let me just go back to the slide. So the question was the operation and the expression at the bottom of the sphere, isn't it expensive to compute for all points? Yeah. So in this case of the sphere, it's not super expensive because it's just like cosine. But for other manifolds like hyperbolic spaces, what will become tricky is that this will become inverse cosine, and it will become numerically unstable near the boundaries of the manifold. So this is a very good question. Sorry, can you speak up?
But that seemed like you consider like a lot of points per second anywhere.
So the question was, is this for every P on the manifold? So this exponential map is defined for every, like it's an injective map. Yeah, so it's defined for every point on the manifold. Every point on the Riemannian manifold will have a corresponding exponential map. And most of the time, it will also have a corresponding logarithmic map. Yeah. So thanks for the question. So the logarithmic map is the inverse of the exponential map. And it's well defined only in a local neighborhood of the exponential map, where this becomes a diffeomorphism. And the idea is the following. If you start at a point Q, and if I was to follow the curve backwards in time, which is the corresponding vector V I would end up in, right? So this is the intuitive definition of a logarithmic map. And the expression below is the logarithmic map for sphere. So you can see the expression is very different than the one for the exponential map, and it's because it's doing something completely different. So the last operation that I want to introduce is this notion of parallel transport. Oh, sorry, this should say parallel transport, not log map. But the parallel transport, the idea is the following. If I have two tangent spaces P and Q, and I want to move the vector V from one tangent space at P to another tangent space at Q, how do I move it so I don't essentially change the vector in some sort? And I'm being intentionally vague about what I mean by change. But the idea is that the inner product between V and W, if you have two vectors over here, if you take this inner product at every point along the curve, it's going to be the change. It's going to be the same, rather. So there's no change in the inner product. So the metric remains the same. So this is the corresponding vector V that's transported along this curve gamma and hits the tangent space at Q. And parallel transport is a unique operation, and it's also reversible, which means that you can take inverse parallel transport, which takes you from a point on Q or a vector on Q and transports you back to a vector on P along the same curve. Right. So these manifold operations seem a bit esoteric, and it's unclear why we need them. And I'll try to tie it back into the generative modeling use case, which is to say that, well, the target velocity in the Euclidean case was just simply ut of x given z. But if you write the actual expression for this, it's the time derivative at xt. So this is a particular choice of the path you choose. And this is essentially telling you, if I pick a straight line between x0 and x1, what is the velocity if I was traveling at linear speed between x0 and x1 at a particular point? So really, the straight line is a geodesic in Euclidean sense. So how do we elevate this in the Riemannian sense? So in the Riemannian sense, we have a corresponding expression, which is to say that we want to take a log map at a point along the geodesic. So log map, remember, it takes you to a point on the tangent space. So this is now a tangent vector, and you want to divide it by 1 over 1 minus t, rather. And that tells you how fast you need to go. So again, straight line in the Euclidean space is a geodesic. And in the Riemannian sense, we have a corresponding expression as well. So how would you actually calculate this in practice? So one example is for the manifold SO3. So SO3 is the group of 3D rotations. So it's orthogonal matrices in 3D. And the logarithmic map for SO3 happens to be the matrix logarithm. And inside the matrix logarithm, the input is a rotation matrix. So how do we take the rotation matrix and transform it back to its corresponding tangent vector? Unfortunately, if you compute the logarithmic map naively, you have to compute this infinite power series, which is truncated with n steps. And as a result, this is a very expensive operation to compute. So even though mathematically it's very easy to define what this is, in practice this could be very difficult. And this is a place where, from a machine learning point of view, you have to make a very conscientious design decision, which is to say that, oh, I can change the representation of my input. So instead of representing 3D rotations as a rotation matrix, I can change it to another representation, which is the rotation angle representation. And the rotation angle representation is just simply this expression over here, which tells you the corresponding angle and the radius in the direction you have to, so a vector's omega and the axis of rotation around omega. And as a result, this is a completely different representation of the same object, but the logarithmic map for this representation is much easier to compute. You don't have to deal with an infinite power series of matrix powers. And in practice, when we do implement things in SO3, we prefer this operation because it's much faster to compute. All right, so now that we kind of developed intuition for how to do the manifold operations, we can now actually formally define how to do inference on manifolds. So intuitively, the easy expression that changes is to, instead of doing addition, we do exponential map at xt. So we compute everything in the tangent space. So ut is a tangent vector multiplied by delta t. And then we take the exponential map to get to t plus 1. Similarly, for diffusion models, we also take the exponential map of the term inside the expression over here. And the other thing to note is that the zt previously was a regular normal distribution. This is now a tangent normal distribution. So this is a normal distribution and the tangent space at point P. And remember, the tangent space is also an Euclidean space. So this is equivalent to Euclidean normal. Right. So the one thing that we still need to talk about is, for diffusion models specifically, we need to be able to compute the score function. And the score function is this gradient of px, or pt of x. But we still haven't defined how to compute the gradient on a manifold. So this is one of the last pieces we need to actually complete the story. So the way we compute gradient is that we want to elevate the gradient operation to be a Riemannian gradient. And the Riemannian gradient has a very similar interpretation to Euclidean gradient. So if you give me a smooth function on the manifold, the Riemannian gradient is the direction of steepest ascent, but critically with respect to the metric. So using the metric g. So the formal definition is that we want to find the gradient, the Riemannian gradient, to be nabla g of f inner product with a vector v, such that it is equal to the differential at that point f, or of the function f at point p. And the vector that satisfies this is the unique vector nabla g, which is at the tangent space at m. So in Euclidean spaces, the equivalent understanding would be it's the directional derivative. However, this definition is a bit abstract. So how do we actually use this definition in practice? So when you want to express the Riemannian gradient in coordinates, operationally, this just means that you take the matrix representation of the matrix of the metric, compute its inverse, and multiply it by the Euclidean gradient. So this gives you an operational tool of how to actually use the Riemannian gradient for actual computations. Because everything about the geometry of the problem is encoded in this matrix representation of the metric G. Similarly, we might want to compute the log density at a point P. So a lot of the times, one of the benefits of using flow matching models is that you can compute the change of variables or the change of log density along the trajectory. But to do this, we need to define an equivalent version of the divergence operation. So just like there's a Euclidean divergence operation, there's a Riemannian equivalent of the divergence operation. And the main idea is very simple. So the divergence of a vector field tells you how much of the vector field is a source or a sink at a point. So similarly, we can compute the divergence just by invoking the metric as follows. So in a coordinate chart, you can essentially take the square root of the determinant of G, which is the metric, and then all you have to do is like correct for it when you compute the term inside the summation by square root det G. And we do it component-wise for each of the different components of the vector field. So what would it look like for Euclidean spaces? Again, so remember, the metric for Euclidean spaces is just identity. So this term would be 1, and this term would be 1 over here. And then you recover the Euclidean divergence operation. So yeah, and machine learning, we prefer to compute this divergence in a chart because it's a very simple operation to just code up. All right, so the summary so far is that when we think about building deep learning on manifolds specifically, we need to take care of certain things. The first thing is that each manifold requires different design considerations. The first tip when we think about this is that you want to pick a parameterization of the manifold that makes it as close as possible to a Euclidean problem. And the reason for this is that we know how to do things in Euclidean space really well, and we want to kind of like be as close to a Euclidean setting so that a lot of our deep learning pipeline works. And then the other thing we want to be careful about is that certain manifold operations may be inherently numerically unstable, especially close to the boundary of a manifold. So you might want to reparameterize or pick a different geometry where such a problem may not persist. And the final, I guess, tip is that at least for manifold use cases, diffusion seems harder to do than flow matching. And the reason for this is that, well, we have to compute the score, which requires the Riemannian gradient. And for diffusion, you have to also define Brownian motion on a manifold. And that's not so trivial to do for certain manifolds. So the real question you have to ask yourself is that when you're doing generative modeling on manifolds, do you really need to do an SDE or can you get away with just an ODE? And most of the time, an ODE will give you more bang for your buck. And finally, there's no canonical Gaussian distribution on a manifold. So choosing the prior is also a design decision. Many people choose a uniform prior over the entire manifold because it's easy to do. But of course, flow matching is compatible with any prior. So you can pick any source distribution and go to any target distribution, which is, again, not possible for Gaussian, for diffusion models on manifolds, because you have to pick a Gaussian-like prior. So I'll take a couple of questions now before we go to live coding. And as we're going to live coding, I want to quickly recommend a couple of Python packages that kind of help, allow you to do this geometric computations a lot more simply.
So I actually had a question.
Go ahead.
Yeah, in your experience, is there sort of problems for which the intrinsic representation actually helps compared to the extrinsic one?
Yeah, so that's a very good question. So the intrinsic representation helps whenever it's hard for you to find a projection from the extrinsic representation. So a lot of the time, the projection operator could be very nasty to compute, or it could be expensive, or you may not have it in closed form. And in those cases, you prefer an intrinsic representation.
So I see. Thank you. Yeah.
But that's a good question. Yeah. And unfortunately, like this answer varies from manifold to manifold. Any other questions before we jump to coding?
Not anything that I see in the chat. So yeah, we can go ahead.
Let's try to code some things. Let's try to connect the runtime. Okay, let's see. All right. It will better? Yeah. All right. So we're going to try to code something very simple, just to give you some intuition for some of the things we've talked about. And the first thing is that we're going to code up, because we talked a lot about it with geometry on a sphere. We're going to try to visualize some of the geometric concepts on a sphere. So the first thing is that we just import a bunch of these packages. And if it cooperates, we will continue. Okay, so it's running now. We'll also use the GeoOpt package, because this is the one package that has a lot of the nice manifold operations that's already written for you, and it's extremely simple to use, almost stupidly simple. So I want to kind of illustrate the beauty of this package, and it's not my package. All right, so as this is running, so we're going to take the first example to be a sphere embedded in RD+1. So this is an extrinsic representation. So by definition, every point in RD+1 whose norm is equal to 1 can be thought of as living on the unit sphere. And to do that, we're first going to code up the inner product on a sphere. So the inner product on a sphere is essentially the Riemannian metric. So we're going to code up the Riemannian metric on a sphere. And the first thing we do is that the Riemannian metric will take in 2 points, so x and y. So x and y are both tangent vectors, and we want to compute an inner product with them. So the first thing I will do is to check that x and y are actually valid points. And then next I will do is, because we're embedding the sphere in RD+1, we can use the metric of the ambient space as well. So this means that the inner product here is extremely simple. And already I see that Copilot is helping me out over here. But it's essentially the regular inner product on Euclidean space, where you do x times y and you sum across the dimensions. And this is essentially what we're going to implement. So it's stupidly simple. And the reason it's stupidly simple is because we've chosen to embed the sphere in RD+1, the ambient space. If we had chosen an intrinsic parameterization, we would have to be a bit more careful. And as a result of this, the norm on a sphere can just exploit the Riemannian metric. So remember, the norm is the square root of the inner product of the vector. So how will we do it? So the norm is product is, so we'll use the inner product function that we've defined earlier. So sphere inner product, xy, and then the norm is going to be the square root of this inner product. And that's simply the Riemannian, the norm induced by the Riemannian metric. Finally, as I mentioned earlier, this manifold is embedded in RD+1. So we need to be able to project to the manifold. So any point on the ambient space can be projected to the manifold by simply taking the norm of the sphere. So actually, I'll just code it up like this. Stop norm. Yeah. So yeah, so I every point divided by its norm, plus some small epsilon to ensure numerical stability, just allows you to project to the sphere directly. So while this runs, now another equally valid parameterization of the sphere is in the polar coordinate system, which is we want to pick two angles, theta and phi, and this allows you to define any point on the sphere by taking a radius r away from the sphere, and then using the angles theta and phi. So if you want to convert between these polar coordinates to an x, y, z coordinate system, what we would do is to say that the first coordinate x is sine theta cos phi, the second coordinate is sine theta sine phi, and the z coordinate is cos theta. And as a result, we can actually use this coordinate system to visualize things on the sphere. So I've already written a function that does this for me, so I won't code it up from scratch. But essentially, what it does is that it plots this shaded version of a sphere or a unit sphere for you. Okay, so now that we've done that, we can also see the difference between this intrinsic coordinate system versus an extrinsic coordinate system. So I have another function over here, which essentially tries to visualize the sphere by generating a lot of random points and then projecting to the sphere by using the dividing by its norm. And as a result, you will see now, it gives you an equally valid parameterization of the sphere. So each of these points is not on the sphere, as you can see. So I picked generated a random set of 1,000 points and then divided by its norm, and I'm on the hypersphere. Okay. So the next thing we're going to talk about is the different manifold operations. So there's the exponential map, logarithmic map, and parallel transport. Each of these are a bit more complicated, so it's easier to code this up with the package geoopt. So for the package geoopt, what I've already done for you is kind of define this class sphere. And as you can see, the exponential map is simply self-x map, where the first argument is the point on the sphere, and the second argument is the velocity you're following to reach the endpoint of the exponential map. And correspondingly, we have the log map, we have the distance, and we have the parallel transport on the sphere. So the beauty of this package is that instead of coding up these equations from scratch, we have simple one-line expressions that give you the entire computation for free. Okay, so given that we have the x map, log map, and parallel transport, I want to define a geodesic interpolant on the sphere. So the geodesic interpolant is the actual interpolant that we will use to do flow matching. So we need to be able to compute this, which is essentially, if you give me 2 points, let's say x0 and x1, what is the equivalent point xt if I follow this path? So the geodesic interpolant, I mean, it's quite simple to code up because we've defined our function before. And it's really, so we want to define xt, and we're just going to brutally copy this expression over here. So the expression says we want to use the sphere x map at point x0. Then we multiply by time t of the sphere log map also at x0 of a point x1. So what is this saying? We're saying that we're starting at a point x1, and then we want to move to x0 along the trajectory of the geodesic that links them together for time t. And that's how we're going to get xt. Okay, so let's actually try to visualize this geodesic. So I have 2 points on the hypersphere, so these 2 red dots, and now I want to compute the geodesic between them, which is going to be a curved path between these 2 points. Right, so to compute the geodesic between these 2 points, what I will do is to say that I will take a discretization of time. So I will take 200 steps between 0.01 and 0.99, and I will compute the trajectory, which is to say that I'll compute the point xt at every point. So quite simply, because we have our geodesic interpolant, we will consume points 0 and 1, give it a time parameter, and compute the trajectory and attach it to the trajectory. So if we do this, we should get a curved path between these 2 points. And this path is the shortest path between these 2 points traversing the sphere. So very simple to do. And if I was doing a flow matching model, what I would do is I would take the time derivative of this path of a particle that's moving along this path. So that was sphere. In the time remaining, I also want to expose you to another geometry, which is not too different than the sphere, which is toroidal geometry. So it's going to be a torus in 3D. So a torus in 3D is very similar to a sphere, but it's geometrically quite different. So we have 2 angles again, so theta and phi, and we have 2 different radiuses, r and like a minor radius r and a major radius capital R. And a torus is essentially the product manifold of 2 circles. If you take the product manifold of 2 circles, you have essentially what's a torus. And to do that, we can kind of just generate some torus data. So I've created a torus for you. And it essentially looks like this. So this is quite a fat torus, and I've generated random points on this torus. And I'm going to do the same trick as before, which is to say that, oh, I want to visualize geodesics on a torus. So what does the corresponding geodesics on a torus look like? Yeah, so the torus is, let's see. So we're going to use the GeoOpt package. And the torus is essentially going to be a cross product between the spherical manifold as well as, oops, this should be 2. So yeah. Oh, crap. 1 second. Yeah, so it's a product manifold between 2 S1 circles, and we're going to make a geodesic interpolant again. So the geodesic interpolant is essentially the same idea as before, but the thing that we change compared to the sphere is that we just change the manifold, but the rest of the operations remain the same. So x map, t times log map, everything else is the same. So as you can see over here, when you do this, you have a corresponding geodesic that takes you from this point over here and wraps around the torus and gets you to this point over here. So same idea, same thing. And that's kind of the beauty of the GeoOpt package, is that it abstracts away all the actual nasty analytic expressions and gives you a very clean interface to code this up. And the last thing I want to mention is that the tutorial also contains a very detailed example of hyperbolic geometry that I will not go through because it's a lot more tricky to explain. But I invite you to try it yourself. There's a lot more cool things over here, such as the hyperbolic inner product. And finally, also the equivalent of Gaussian distributions if I run everything. So equivalent of defining a Gaussian distribution on hyperbolic space and how that changes based on the geometry of the problem. So that's kind of where I want to leave you all. So I will take any further questions if there are for this part of the tutorial. If not, I'll pass it on to Alex afterwards. So there is a question in the audience. Could you please tell me which part of the code you were talking about?
I'm actually not sure if the audience is allowed to unmute themselves to ask question,
Okay.
but I think their question is, are there cases other than SO3 where the matrix representations have less issues on the logarithmic map?
So SO3 is a broader class than what I described. So SO3 is specifically a Lie group, and for all Lie groups, the logarithmic map is the matrix logarithm. So you will have issues computing the matrix logarithm for any Lie group. So not just SO3, any SON, ON, and other stuff. But that's a good question.
There's another one that the Euclidean geometries are preferred because we have better intuition, but are spherical and harmonical systems also well understood. But I'm also not sure what harmonical means here.
Yeah, I'm not sure about the question, but I think the Euclidean geometry is preferred because of the numerical stability it offers. So if in those systems like harmonical, there's equivalent numerical stability, I would imagine it's okay, but my intuition tells me it won't be. So
actually they meant hyperbolic systems.
Okay. Yeah, so hyperbolics, yeah, so that's a very good question. So in hyperbolic geometry, what I didn't go through, and you should definitely try going through this on your own, is that we have to do a lot of additional tricks to make things numerically stable. So for example, you have to clamp more aggressively. We have to also have a smaller epsilon value because we're dealing with hyperbolic sine and cosine functions, and they blow up really quickly. Because the reason they blow up is because each hyperbolic sine and cosine function is going to be like e to the power x. So the value of x controls how big the value could be. So if x is greater than 40, you cannot express it in floating point precision. So that's why we have to clamp these things. Yeah. I hope that answers that question. Okay. Cool.
Yeah, I don't think there are any more questions.
Cool. All right. In that case, I will pass it on to Alex. And Alex, if you want to share your screen. Cool.
You turn off your audio. Can you hear us?
Yes.
Perfect. Thanks. Okay, let's see. Where did my cursor go? Cool. Okay. Yeah, so this is the third part where we're talking about how to match these things together. So the geometric part and the generative model part, and we'll mostly focus on flow matching things because, well, I think it's the easiest one, but we can talk about why that's the case in a bit. So I'm going to talk about sort of applications and sort of categories of applications where it's sort of easier, where it's harder. Then talk about how to go from the Euclidean case of flow matching to Riemannian flow matching. And then look at sort of a case study in protein design, so in particular AlphaFold 2 and how they sort of represent these types of manifolds in proteins, because that I think gives us an interesting idea about what coordinate spaces are useful, when intrinsic and extrinsic are useful in practice. And then flow matching on a torus. This is one of the cases in proteins, but it's sort of it's very easy to visualize, so we'll go through that one with code. And then finally, think about sort of practical tips for these types of models. Cool. Yeah. So we looked at the slide, but basically the first category of things are where you have a nice logarithmic map and exponential map, and you can parameterize geodesics, and everything is fairly easy, right? So it's these types of nice parameterizable manifolds are very. Why did everything appear again? Okay, I see. Yeah. So this sort of first category is I would say most of the focus on geometric generative models. It's much easier. The second category. is on these non-parametric models. So like where it's data-driven or not easy, sort of not easy shapes, right? So it's sort of much harder to parameterize. Well, where's the exponential map, right? What is the geodesic, right? So these are also very interesting and data-driven. So, for instance, one of the things I'm very interested in is in single cell. So we know sort of data-driven manifolds are quite interesting, but much harder to deal with. So I think these sort of geometric generative models will mostly focus on the first case, but then I'll sort of give hints on how to do the second case. Okay, cool. So Euclidean to Riemannian flow matching. Okay, so this is sort of notation. Reminder, Z is sort of the conditioning. So we're picking endpoints here. So that's a tuple x0 and x1. Q is the distribution over x0s and x1s. So most of the time, this is independent. This is what this says, is you pick x0 and x1 independently. And then in Euclidean, the easiest way to do this is just to take a straight line between the two, take a convex combination with regard to t, and linearly interpolate. And so when you do that, then you get a velocity that is very easy, which is x1 minus x0. So here you have depicted, right, you sort of pick two random points from your distribution, and then you pick an xt in the middle, and you have a vector field that goes from x0 to x1 in a unit time. Cool. Okay, so for Riemannian flow matching, we'll use the same first two parts. So we'll take an x0 and x1 in the Riemannian setting, and exactly what those objects are, it depends on your coordinate system. But here's the sort of x0 and x1, and then you take the same independent distribution. And then the interesting part begins is how do you take xt's, right? So this subtraction and addition operations are not defined on Riemannian manifolds, as Joe is saying, but instead we have to use the exponential map and the logarithmic map. So this is sort of the formula for xt, and I'll give an intuition what this means in a second. And then for the flow, what we have is log xt with respect to x1 and then 1 minus t, right? So, okay, so why is this sort of the right thing to do? Okay, so on a sphere, you can look at the interpolation between x0 and x1. Okay, so what is this sort of saying, right? So I think of it as, well, okay, maybe it's easiest to visualize in the Euclidean setting. So for Euclidean, we know that the exponential map is just a plus b, and the logarithmic map is b minus a. And so you can rearrange these things, right, into a form that looks exactly like Riemannian flow matching. And so, right, if you take the exponential, you sort of get the, well, x0 plus stuff, and then you get the logarithmic map, which is t times x1 minus x0. And so this is sort of the same formula, right? You can rearrange this back into the original sort of convex combination. And so this is sort of the intuition is basically you're starting at x0, you're adding t times the flow that you would need to get from x0 to x1 in time 1. And then that's to get your xt, right? So sort of move for t amount of time in the direction of x1. And then for the flow, you say, well, okay, I want to go from xt to x1 in time 1 minus t. And so that's the flow computed with respect to sort of xt and x1. And so this is how it works in general. In specific cases, right, there's many ways to parameterize these maps, so it sort of depends. But this is the way. And so just one thing, right, is this requires very efficient evaluation of your exponential and logarithmic maps. So that's sort of a lot of the tricks are, well, how do you do this efficiently? And well, some manifolds you can't, right? So if you can't do this, what do you do? Well, you have to do something more complicated where you integrate xt over time, and then you analytically calculate sort of the xt dots, so the ut here. So yeah, that's the sort of, this is the basics. All you need to know sort of to go from Euclidean to Riemannian flow matching is to go from this first half, which is sort of very simple convex combinations, and then use the exponential and logarithmic map instead. Cool. So do I have any questions before moving on to this part? Yeah, cool. Okay. Yeah, okay, so one piece that we were thinking before is this sort of log likelihood computation, right? So in the Euclidean setting, it's very useful to figure out the sort of log likelihood at time 1, given your vector field and your prior. And so this sort of gives you the calculation, but it requires, right, the divergence with respect to the metric. And so you can use the Riemannian divergence to calculate the log likelihood at any time using this sort of formula, right? So in the Euclidean case, this simplifies because determinant G is just 1, and so you get the standard determinant form back. And so this is sort of the right? All you need is, well, you can do flow matching, and then you can calculate log likelihoods if you would like using this formula. Cool. Okay, so we sort of talked about just how you go from Euclidean to Riemannian flow matching, but how is this sort of useful in practice? So I'm going to talk a little bit about protein design and the representations there, and then we can look deeper into sort of the different choices you can make. Okay, so protein design, basically, we're trying to design proteins, which I'll describe in a bit, that are sort of satisfy some properties. And so that's the idea here. Why to do this? Well, proteins can do a lot of interesting things, mostly medicines, vaccines, maybe for climate change. We'll see what the applications are, but I'm very interested in this, so we'll see. But okay, so what might you want to design for? So there's sort of many objectives, and you can think of them as sort of all functions of the structure and a little bit of the sequence. And so what does that mean, right? So you sort of, there's a function you want to optimize, and then you want to generate structures that satisfy these properties. Okay, so, well, what is a protein? I guess that's the real question. Okay, so what are proteins, right? So they are, we sort of name them as sequences because they're sort of repeating patterns of molecules. There's a lot of them. Well, there's sort of a lot of combinations, right? They're built up of this 20 amino acid building blocks, so sort of sequences of 20 different vocabulary size 20. And then you sort of, the sequence folds into some structure, and that has some function. That's the idea. And then that sort of does something, and you would like to figure out, well, let's make a new protein, and what does it do? Okay, so, but how do we represent proteins? Okay, so proteins are really these very long strings, long molecules that are chain-like. So there's the sort of backbone of that forms a sequence, and the sequence, what the sequence really tells you is what the side chain is. So what hangs off the ends. And so what does that mean, right? You sort of have this couple of representations. One is sort of a cloud of atoms. So the first is like you could look at the 3D coordinate of each atom location. And so this would be a sequence of length n, and there's about 19 atoms per amino acid if you count the hydrogens, and 3 coordinates, right? So you could represent them in Euclidean space, and we could in fact do Euclidean flow matching on all of this, or fusion, right? Whatever. In fact, this is actually currently done also this way. So we've talked about that in a bit. And so the other way we represent this, I think, which is very interesting, is sort of is a set of reference frames in SE3. So sort of a central location for each amino acid, and then a rotation around it. And so that tells you sort of the orientation of the backbone, and that's the sort of these triangles here. So that's the sort of main pieces. And then you also have the side chains. And so here you have sort of a series of rotations off of the main backbone. And so this is a series of torsion angles, right? So that's what these little green things are representing here, is how rotated they are relative to the previous torsion angle. Okay, so why would you ever choose this sort of crazy representation? Okay, so I guess there's a couple of reasons. Okay, so this is just a different representation, right? There's 20 different amino acids. You sort of have different colors for different types of molecules and different lengths. And then the backbones is sort of parameterizing where the C alpha atom is, so the main one, and then the rotation around it. But so why would you want to do this representation? Well, there's a couple of reasons. I think one is that, well, it's I would say it really only enables us to use our prior knowledge about how these molecules are structured. In particular, right, we know these bond lengths pretty much precisely, right? So instead of having to figure out exactly how distant these two bonds are, you could say, well, I know exactly how far they're away from each other, and sort of rotate it around and figure out, well, where should it be relative to the previous one, and not have to figure out in 3D space whether it, well, is too far away or too close, right? And so that's one reason. I guess another is that, well, this is sort of a bunch of independent components, and so this is sort of easier to learn from a machine learning perspective. So you could also parameterize this, for instance, as sort of all torsion angles. You could do torsion angles for the backbone too, and then you would have a long series of torsion angles for the entire thing. And this is a possible representation, but it's not as good because it's very global, right? So if you make a small change in one place, then it can change things all along the protein. So you change a small angle somewhere, and it may clash in another place. And so this is sort of harder to learn too. So this is sort of twofold good, right? You have very independent, but also built in our prior knowledge about structures. Great. So, Okay, so AlphaFold was a model, well, and helped win the recent chemistry Nobel Prize that goes from a sequence to a 3D structure. We're mostly going to be talking about this last part, that's the structure module. And that's the part with a lot of geometry in it. Everything else doesn't really have much geometry. It's mostly big embedding spaces, either sort of the length of the protein or the length squared of the protein. So that's sort of the main processing components, but the last part is sort of use the geometry that we know about proteins. So that's what builds in this sort of SO3 and SO2 space. And so, okay, so what does that look like? Okay, so let's see. Okay, so why do we care about this, right, in terms of the generative modeling framework, right? So AlphaFold 2 is not really a generative model, I would say. It goes from a sequence to a structure, although you could claim it is in some ways, because it sort of starts at an initial structure and then does 3 steps to refine that. So maybe a conditional generative model. But the real reason that we're interested in this is because almost all of the protein generative models right now use the same structure module as the backbone of the network to sort of think about 3D space. Cool. So okay, so the structure module of AlphaFold 2, right? It takes in backbone frames and a representation of the protein in sort of a single and pair representation, and outputs updated backbone frames, and then also angles for the side chains. Right. Okay. So, and this is the code for it. Okay. So thinking about this a little bit, right? We have sort of S as single representations, Z as pair. We take in sort of these identity ridges, and then we slowly update the ridges, and then we have a sort of angle resnet, which takes the current representation and gives you angles back. And so at the end, you just get angles and updated ridges in this very nice form. Okay, so but we can look at exactly the shapes here, right? That's sort of interesting. So the ridges here are represented as n residues by 7, and the angles are 7 by 2. Right, so these sort of seem just like magic numbers, and I'll explain where these come from in a second. Cool. Okay, so why are they calling ridges? They're calling them ridges. Ridges here are elements of SE3. So that's a translation and a rotation. And so the 7 comes from the translation part being R3, and a rotation part being quaternion, representing a rotation in SO3. And so what's interesting here is, right, it's directly saying here's 7 coordinates for the sort of the thing on SE3, and I'll output those 7 coordinates, right? So that's sort of the, treating these as intrinsic parameters of the model. You're outputting a rigid directly. Okay, so the second part is angles. So angles, right, are SO2, and so, right, they're just rotations. Okay, so what's interesting, right, is that there are, okay, so there's 7 rotations here. But why is it outputting this extra 2 dimensions, right? Well, it turns out what AlphaFold actually, why can't I see my, okay, maybe we'll get rid of this. So it actually predicts sort of a point in R2 and then projects it to the unit circle. So this is a very interesting parameterization, right? So that is one choice you could make. So, and why do they choose it, right? So they choose to predict a point in just R2 and then project to the circle instead of, say, directly predicting a point on the circle. So this is another choice that you can make, right? So this sort of gets at, well, what parameterization should you pick for your manifold? And so we'll sort of go over exactly why they might have chosen this in the next steps. Okay, so yeah, so here, right, what you do for the angle resnet is you take in this representation. It's sort of a residual network, and to get the projection, you divide by the norm, and so that all that does is just give you a point on the unit circle, which you could always transform into a torsion if you would like to. Cool. Okay, so flow matching on a torus. Okay, so the torus is interesting, right? So what do we mean by torus? So this is sort of the one-dimensional torus, right? Joe is mostly showing the two-dimensional. That's how I would tell us. And of course, AlphaFold is using 7 dimensions, right? So, okay, so what is the right parameterization for this kind of thing? So there's sort of many choices, right? So one that's nice is, well, you could parameterize rotation matrices, so a rotation around sort of the center coordinates as a 2x2 rotation. you could also directly parameterize how far you are along the circle in terms of movement in radians, or you could do this other thing, right, which is predict a point in R2 and then project down, right? So these are really the different questions is, well, you know, which one should you pick, right? I guess is the question. And I think it depends on the application, and we'll go through sort of, well, which one might be good in what setting. Okay. Yeah, okay, so now we will go to sort of coding the torus, and I'll sort of show you how to code from the Euclidean example that Kelly had to a Raponian flow matching on the torus. And think about the parameterization of the torus and the parameterization of the vector field. Cool. Okay. It does not give me my cursor. No. Okay. All right, so this is the same notebook that Helly was showing. So you can see, right, we have this MLP, zoom in, yes, okay, excellent. Okay, so we have a MLP, right, which, and we have the same model. Okay, so if you run this on the log in 2024, well, you get, you sort of get distributions changing over time, right? So that's what we saw a little while ago, is how to transform this. And so now we'll see how to use this and get the Riemannian setting. So, okay, so in the torus flow matching, so the first thing we're going to do is there's just a little change in the data set, right? So, okay, so here's just some nice plotting functions. This allows us to convert between spaces. So sort of how do you make a surface of the torus in 3D and then visualize it? And okay, so this is the part where we start. So okay, so we take the same torus distributions we had, we do some sort of multiplication and moving it around to get it in the right places, and then we can visualize it. So same looking log to 2024, but then we can also visualize on the torus in 3D, right? So there's many different parameterizations of the torus, right? So this is sort of a projection on 2D, right? So this is looking at the intrinsic coordinates in 2 dimensions and looking at them. So this is sort of, think about it, if you wrap the thing around the top and the bottom, that's what you would get. And this is the visualization in 3D. Where did they go? Okay, I'm somehow deep inside the torus. Yes, well, there is a torus here, but it seems I can't zoom out. And trust me, there's a log in 2024 here somewhere. Interesting. Top right? Ah, okay. We will zoom out, hopefully.
Alex, maybe press the home button. It should like reset the home shaped button.
Excellent. Perfect.
Yeah.
Thank you. Okay, yes, this is excellent torus. And so, yeah, okay. So, yeah, there's the 2024 on top and the log on bottom. And so I put these here because, well, if, sort of the log is near the bottom of negative pi, and the 2024 is near the top. And so there's sort of many different ways, right? So all we require from flow matching is that they match the distribution at time 0 and then match the other distribution at time 1. So there's sort of many flow choices we could use. And so, in fact, we can use the Euclidean flow on the torus, right? We can use the Euclidean flow in the intrinsic parameters of the torus and still get a valid answer, right? So this is the first thing we're going to do. Okay, so I'm going to define a couple of useful things here. So this is a symmetric modulus, which is, we'll use that in a sec. That's not used yet. And here's the sort of, this is how you would do it in Euclidean, right? So let's define the log map of Euclidean, right? It's x1 minus x0. And then we can calculate xt in the Euclidean setting, right? Which would be using that formula in the slides. We have, let's see. So we have this, and Okay, so looking at this. For Riemannian flow matching, right, we're defining xt as, well, sort of, in this case, x0 plus t times the log x1 minus x0. So this is log x1 minus x0. And so this is the correct xt, same thing as doing the equating setting. And the get ut is also the same, right? So all we do here is just reformulate the sort of the simple this way into something that looks like a log map, so that when we change the log map and the exponential, then we'll get to torus flow matching. Okay, so this is exactly the same. So I'll start running this and the same parameterization. So right, what is this doing? This is basically pretending that we're in 2D, right? We're just projecting the torus into Euclidean space and then doing flow matching. And because flow matching doesn't sort of go outside of the torus, we're just still moving along the torus, but we won't cross this sort of pi to negative pi boundary, right? So this is sort of interesting, is we'll get a flow, but we won't sort of go the fastest way. We'll go around in terms of the Euclidean setting. Okay. So this is running. Oh, wait, I better, sorry. It's not running because I did a hacky trick where I just time sleeped so that it wouldn't die. Let's see. Yes, okay, so I'll try this again. Yes, okay, so we're running this. Yeah, so because in the beginning of this thing we lost the T4, and so we couldn't yeah, that was a problem. Okay, so this is running, and we'll see sort of what the Euclidean flow matching, if you were to do it, looks like on the torus. And then we can start coding the how you do sort of Riemannian flow matching with the X map that's sort of correct and does geodesics. So this one can sort of cross the boundary of pi to negative pi and go around the other way. Okay, so yeah, so Euler integration is the same thing. We'll also use the same Euler integration for this. And then plot it. Cool. Yeah, so this should be done shortly. And then we'll talk about the changes you need for the other, for the torus. Okay, so yeah, well, we'll start talking about this. Okay, so for the torus, what might you need to change? I would say, so the log map definitely is going to need to change, and then the computation of xt is going to change. And I think the computation of ut probably it shouldn't need to change. So and we'll see why that is in a second. Okay, so we should be done here. Okay, so yes, so we have the flow now. So okay, so this plots the trajectories, right? So we started at the LoG, and then these plot sort of the trajectories, right? But we noticed that the L should sort of go, if it was going the closest way, it would go downwards and around sort of the boundary here. And yeah, so we can see this in the sort of different types of animations. I guess the interesting one is this 3D on the torus. So we'll see this in a second. But I guess the basic idea here is, well, it really doesn't matter. Like, flows are nice because you can choose whichever one you want, and as long as it matches, then you're good to go. So is this one easiest to learn? That's the next question, right? And probably not, but yes, we'll see. Okay. And this always runs slower when people are watching, so let's see. Okay, delete this guy. Okay, so yeah, you can see two things here, right? So the animation, we can see the moving up, and then for the torus, we can see that this sort of goes the long way around. So the sort of the inside, there's nothing, but it goes sort of around the outside of the torus here. Okay, cool. So how do we get to Riemannian flow matching? Okay, so for this, we're going to use this symmetric modulus function. Okay, so what is this actually saying, and why do we need? Okay, so our x0 and x1 are values between negative pi and pi. And what we would like to do is sort of go the correct direction around the circle, right? So we have 2 points, x0 and x1. And if we do what we currently do, then we always go in the same direction, right? So if this is the boundary between pi and negative pi, when we do x1 minus x0, that means we will always go in around the circle this way. So all the vectors, even if you were, say, here and here, you would go around the circle this way, right? So that would be a very long flow. And so what the symmetric modulus does, so we added here, is picks the right way. Okay, so well, this math is a little bit complicated, right? But so think about the case where you have x0 is like a little bit above 0, and x1 is a little bit below 0, so like near negative pi. Then we get a little bit, so we add the two together, and it's, well, just about, well, it's a little bit more than 0, right? It's sort of like, 2 epsilon over 2, so just epsilon mod 2 pi minus pi. And so this is why you might want to do this, is it sort of basically says which direction is closest and points the arrow in the closer direction. So you should have 2 choices, and that goes the right way. So yeah, that's the first thing we need to do. So this is log map, which tells you how to get from x0 to x1 as fast as possible on the torus. And then the other part we need to do is add a symmetric modulus here, which says, well, no matter what I want to do, I want to keep in the range of pi to negative pi to pi. And so these should be the only 2 changes we need for this, and we will start training again. And so UT doesn't need to change, right? So what does UT say? It says take my current XT and take my current X1, which are both locations on the unit circle, and then does a log map to say, well, which direction is the fastest, and then says I should get there in time 1 minus t, right? And so effectively it constructs sort of this vector, and then says I would like to get there in some amount of time, in the time remaining, essentially, in 1 minus t. Okay, so while this runs, okay, so all we need to do to change this function, so since we're using these 2 coordinates, all that needs to change is we need to make sure that it stays within pi, negative pi and pi. And so we just need to add this symmetric modulus here, which says, well, take my sort of xt update and, well, clip it, sort of wrap it around if you need to. So if you go outside of above pi or below negative pi, then it'll just go back in the circle. Cool. So that defines sort of the Euler integration on the circle instead of on R2. Everything else is the same, except we need the wrapped. Okay. Yep, so this should be finishing up. Okay, so it looked like this before, where we went sort of, well, pretended it was like Euclidean space. But this one should pretend it's like a torus and go the shorter way around the torus. Okay, and so here's the updated plot. So you can see the LoG now goes down, or mostly goes down and around, and then back up to the top to the 2020. Yeah, here we can animate it. And then we can plot on the torus again. Yes.
Do you have intuition for why some points when
Yeah, that's a good question. Yes, sorry. So Jacob was asking sort of why some of the points go the long way around. And so that I would say it's because some of the points, it's the closer way to go around, basically, right? So if you're going from the very top of the log to the very bottom of the 24, then it's closer than going sort of around the other way, right? And so depending on exactly where they are placed, then you would go this way, right? So one of the interesting things is, right, like these seem very strange, and maybe you want to do sort of more shorter paths on average, right? So this does not give you sort of optimal transport paths, but if you did a pairing that was sort of related to which points were closer overall, instead of an independent pairing, then you would get paths that went sort of probably all the way, all around that way, the closer way. And so, yeah, it's, I guess it depends on where they are. So if you move the log up a little bit, then it'll probably shift and half will go each way, basically. So it's sort of a mix. Yeah. Cool. Yeah, so we have the animation, and yeah, you can see that some split up and some split down. It's kind of interesting to sort of do a bunch of mixing, and then they all appear in the 2024 and slowly gain resolution again. Cool. And yeah, you can see the trajectories here, right? They look very different. Instead of going around the outside, most of them go through the inside. Yeah, and the 2024 here looks fairly ugly, but I think it's just because it's squished. Yeah. Cool. Okay, let's see. So yeah, there's this. Okay, so that's the main thing is this. So I was going to talk a little bit about parameterization. So there's a couple of different ways to parameterize these functions, right? So here we say, let's make our network output something in 2 dimensions, right? And this is going to be something, well, we're going to clip it basically between to match the UT, right? So this, what is this? This is sort of outputting something in the range of the logarithmic map of the unit circle, right? So that's saying it should be sort of, it's outputting a velocity vector around the circle. So it could be either going, if it's positive, it's going this way, if it's negative, going this way, right? But it's sort of outputting in the tangent space, well, of the manifold, which is kind of interesting. But you could parameterize it other ways, right? So you could also parameterize it so that you predicted the x0, for instance, right? So instead of using this as VT, we could say instead that the model outputs x, sort of some predicted x1, right? So if we did this instead, then that means, well, this is sort of target prediction instead. Then we could do, and then we could calculate VT. So then VT, right, would be, well, we could use the same get UT function, right, which says how fast would I need to go, right? Get me the vector that takes me from xt to x1 in time t. So I can use that function again to say VT should be equal to get UT to get me from xt to x1 pred in t amount of time, right? Okay, so this is a very small change, right? But now it's very interesting, right? Because our model is outputting something on the manifold, right? So a point on the manifold, and now we're calculating the vector to get there, right? So this is a different type of parameterization, right? It should it's interesting because, well, oftentimes for different kinds of manifolds, it's easier to predict something on the manifold rather than the tangent space, right? So this is a common trick is, well, we have, for instance, like many models that are good at outputting the object directly, but not so many that are good at outputting tangent space. So in fact, for protein SO3, for instance, almost all the models try and predict the sort of nice looking protein predicted x1, and then calculate the velocity to get there in t amount of time. And so, and that's just because of sort of numerics and how do you parameterize these models and leveraging sort of existing work to parameterize and predict sort of molecular shapes or whatever manifold shapes you have. Yeah, so this should work exactly as well. So now you have a VT, and this allows you to parameterize your model this way. And the final thing, right, would be to change it so that you predict regress against x1 directly. And so instead of doing a loss here, you can instead do a loss that was on the x1 pred. So if you did instead x1 pred and x1, and oftentimes you want a scaling factor here. So It turns out that in Euclidean space, the right scaling factor is sort of 1 over t, 1 over 1 minus t. In manifold space, it's much less clear. Oftentimes, it's very unknown, but that's sort of a heuristic, right? It's sort of one of these loss weighting things. All of them should converge. It doesn't matter, although some of them should work much better than others. So you can always sort of do this trick where you predict x1 instead, and oftentimes it's easier to get losses in this space than others. So for sort of the torus, it doesn't matter, but more complicated examples might. Cool. Yeah, so that's what I wanted to say mostly with this example. Is there any questions on sort of this thing before I move on to sort of best practices? Okay. Okay. All right, so yeah, we did a sort of parameterization on the torus, parameters of the vector field. Okay, so some ideas, right? So Euclidean Riemannian, it's very easy in this simple torus space. The torus can live on many dimensions. So we showed a 2D plot, a 3D plot, but also you could do a 4D, for instance, right? If you parameterize these sort of unit vectors. And so if the network, for instance, outputted sort of 2 by R2, then you could also get 4-dimensional. So sort of many different extrinsic representations of the torus. Let's see. So some parameterizations are better, I would say, for code because, well, you make fewer errors. So yes, you could do this rotation matrix, and in fact, there are some tutorials that way, but oftentimes it's harder. Some are easier, right? Some are more stable, and the best one depends on your sort of application. So whether intrinsic or extrinsic, I would say in torus, mostly people use the middle one and the one on the right. I would say the middle one is nice because it's very simple, right? You output exactly 1 dimension per torus dimension, but it has sort of this discontinuity at -pi to pi. So some people are worried, right? The network sort of needs to say the same thing is going to happen at pi, -pi, and that's oftentimes a little bit hard to enforce. So what's nice about unit vectors is there's no sort of discontinuity, right? So you're doing it this in 1 higher dimension, everything is smooth, and so although you do have to output twice as many dimensions, right? So, well, memory constraints, well, code, something like this. So I guess this is one of the reasons why you often do 1 higher dimension is to make it smooth, right? So sort of you could do in the middle dimension, but oftentimes it's not very smooth when you have a closed manifold. And so in fact, that's the same thing that's happening in the AlphaFold 2, right? Right, so SO3 can be represented in many ways. Quaternion is one of them. And one thing that's nice is that it's very smooth. You could also represent them as a thing in R3, the sort of axis angle representation, but this also has a discontinuity. So oftentimes it's better in practice to represent in 1 more dimension, everything is smooth, than trying to minimize dimensions. Yeah, so I think it's a careful balance, right? So SO3 can also be represented as rotation matrices and are in 9 elements, right? But well, that's many extra elements. So it's sort of a balance on what you take. So sort of smooth, but fewer things is probably right, but not 100%. Cool. And so yeah, the final thing is vector field parameterization. Most of the code that I've seen is oftentimes doing this target prediction. So you have a network outputs the x1 and then calculates the vector field to get there in the correct amount of time. And so this can be equivalent in many senses, especially in the Euclidean space, both analytically and practically. In Riemannian spaces, it's almost never equivalent analytically, but is often learned just as well. Yeah, so choosing, right, this is sort of whether you do an intrinsic versus extrinsic parameterization. And I think sort of choosing the smooth one is probably best, although for, well, examples, it's often easier to do lower dimensions. Okay, so going sort of practical conclusions, I guess Riemannian spaces, we're mostly preferring flows, and that's because diffusions are really hard to define, except in very simple settings. It's much easier to find paths than diffusions. And this sort of manifold spaces, they're parameterizable ones, which is the ones we mostly talked about today, and then the ones that are not parameterizable. And those are much harder. as far as we know. And finally, the parameterization really matters. So I can show you an example of what doesn't, but generally making it more Euclidean is good. Okay, so here's an example of what doesn't work that I was trying to code. Okay, so equivalently, right, you should be able to do this parameterization of x, y and project. And so I made this XY MLP before this. And all it does is instead of, it outputs sort of twice the dimensions, right? So that's a point at R2 for every dimension of the torus. You can normalize it and then get sort of the predicted theta back, right? And return the vector field. And so, yes, this in theory works, but in practice works very poorly. And so I think this is sort of a numeric thing, right? Because, well, you're differentiating, you're backprogramming this arctangent, this clip, right, and this division. So, you know, maybe there's a problem here, right? So you could definitely do this better, right? But this is a different sort of parameterization for the torus. Same things apply. But when you do it, it just sort of collapses, right? So, well, the different parameterizations definitely matter a lot, basically. And so, you know, while many things should work, the training is sort of the stable training, I think, is the hard part. And it sort of is a little bit of playing around to figure out what works best. I don't think anyone has sort of a general rule on exactly how you parameterize these things. But, well, I guess the closest you can get to a general rule is like this, making it more Euclidean, making it more like mean squared error is sort of the best you can do. And so that's the general suggestion, but it depends on the application. Okay, so yeah, final thing I want to talk about is sort of, well, what is there that we don't know how to do, and what are sort of the open questions. So here, let's go back to this. Okay, so one of the big things is sort of, do you need this equivariance, right? So AlphaFold 2 has all these equivariant pieces built in. But if you look at AlphaFold 3, it in fact removes them and directly parameterizes the sort of representations in Rn and then the atoms in their coordinate space, right? So they totally skip this. And well, this was sort of you know, it's a question of whether you need equivariance at scale, sort of. And I think this is still a very open problem. Some people have opinions either way. And, you know, this is, I guess, under debate exactly when you would need sort of these types of models, especially when you scale up. Because you can sort of softly enforce equivariance in other ways. Yeah, and so this parameterization piece, I think, is the key of many of the geometric generative models. How do you sort of parameterize the model in a stable way? And learning dynamics, nobody really has analyzed carefully, I would say. There's lots of tricks that people use, but nobody says like why this really works or has looked at lost landscapes or anything like this that I know of. So this, I think, is an interesting question about, you know, what sort of parameterizations can we get better at figuring out a priori what sort of parameters you might want to use for your specific problem. Yeah, so I guess this is getting back to the first part, but when should you move the when should you sort of use these tricks versus just, you know, parameterizing in the ambient space or trying to embed in the ambient space if you can and doing it that way. I guess, you know, it sort of depends if you want sort of this constraint or if you want to softly enforce something potentially, how much you need this to be the case. And then, yeah, sort of, well, Joey's been asking this question for a while, but, you know, what are we going to do after flows and diffusions for this thing? So I guess this is a good question is, can we get sort of more efficient architectures, right? So there's some problems with the current models, especially in terms of, well, how do you do inference quickly, especially on Riemannian manifolds? It's very unclear if you can do sort of better than many steps. And the final thing is sort of these non-parameterizable manifolds. I think they're very interesting ideas about data-driven manifolds, but we don't know how to do it very efficiently other than sort of integrating ODEs and matching them. So still very useful, but not as efficient as when you have these nice parameterizations. Cool. Yeah, so that's the end of what I had. I guess we're quite early, but so it goes. Thanks. Any other questions?
Hi, Alex. There is a question on Slack.
Okay.
Adris, I can say it loud so everyone can hear it. Adris says, A question from the third coding section of the tutorial that for
Yes.
points on the cat locus of the torus or for any generic manifold, how do you
Yes.
determine where these points go? Do you make any systematic choice or does any arbitrary choice make sense?
That's a great question. I mean, in this code, we do whatever the modulus of Python does, right? So we specifically, let's see, oh, stop sharing screen. Sorry, I'll start again. So in this case, we just literally use the modulus operator of Python. I believe that says if you are exactly 0, then you stay positive. So it should be that like anything that is exactly on the border goes towards the positive side. But in practice, right, these are real numbers, so it pretty much doesn't matter what you do on the exact boundary. Yeah. But right, there is sort of this problem in that your parameter is setting the manifold, and it should, in theory, if it learns correctly, sort of do something very smooth and Lipschitz on the border. But in practice, of course, you can look at this, and this is not always the case, right? So, yeah, could be better permutations. Cool.
Maybe I can add a bit about this issue. So, since you have these points, like the cut locus of the torus, so your conditional flow would be would have a discontinuity on this point of the cut locus. So in general, this violates the conditions that you need on the velocity field for everything to be well defined. But in practice, since we're using neural networks which are smooth, typically if you use a smooth activation function, then it kind of averages out in the learning and in the smoothness of the network. So that's like another point to add about these discontinuities. I mean, you could treat this thing by, zeroing out the velocity field around these points and smoothing out the behavior around there. But I think that in practice, I don't think that anyone has seen like a critical effect of this because these typically are zero measure events. So they don't affect much the outcome of the generative model. So.
Thanks. Oh,
Yeah, he
else?
says, thanks for the answer. Does anyone else have any question? You can ask on the QA on Zoom, on the chat, also in Slack. So we are tracking questions then. They do follow-up questions for Hali, based on the previous question. Does this also applies for singularities?
What do you mean by singularities? Maybe he can write in this class.
Yeah.
All right, it's a telephone game.
I guess they are listening to the talk, but anyways,
Yeah.
In the meantime, someone asked for the code and the slides. I think Joy already sent it in the tutorial Slack, but they will be also available, I guess, in your website.
Yep.
Yep.
Mhm.
So it will be publicly available.
Cool. Okay.
Yeah, Adris is answering right now. So in the follow-up.
Ah.
Okay, you have access to it. Okay.
Can you see this, Holly?
Yeah, I can see it.
Yeah, we can see it.
Okay.
Yeah. So I guess these are similar issues to what happened in the torus, for example. Because I mean, on the sphere, that's where the example of the Hierarchical theorem is that you cannot have a velocity field that does not zero out at any point. So for the specific instance of a sphere, I think you could also do something like what I suggested previously of smoothing out your conditional flow around the singularity points, which are in this case would be like the cut locus on the sphere would be the antipodal point for an x1 point that you condition on, right? So you would have an issue only on the antipodal point. So then again, you could it's a bit artificial, but modify your conditional flow so that an epsilon neighborhood of that singular point will not flow to x1. So it's like we would also have a non-zero density on the sphere. Because the current way to what it does is like, imagine that you start from the antipodal point and you just kind of shave the sphere all to x1. So we actually have areas where the conditional flow is not defined, and also there's zero density conditional. So you could smooth it out. And again, I'm not sure how much of a practical relevance it has, but maybe it does incur some issues. Does it answer your question, Nadrish?
Yeah, I think it does.
Yeah. Okay. That's funny. This setting. Great.
Great.
All right.
All right. So I think if there is no further questions, yeah, we would like in the name on behalf of the organizers just to thank all of you, to the tutorial organizers like Joy, Heli, Alexander, the three of you, for like a nice tutorial, which is like 3 hours long, but we know it's a lot. But there was different parts, it was self-contained, easy to follow, and also with a lot of code, but I think that it's also really valuable in the field. We would like also to remind the people that there is a feedback form for the tutorials that I will send it right now in the channels, like here in the chat, and it helps a lot both the tutorial organizers and also the meetup organizers to know how we can improve like the experience, especially this virtual experience. Yeah, thank you very much to all of you.
Thanks.
Thank you.
Yeah, and we will come back in 15 minutes, like in the clock time, in a bit more than 15 minutes with the next keynote session by Zachary Ulissi. So maybe we can have just a break right now for 15, 20 minutes and come back at 6. Well, I'm in Europe. It was 6, so in 20 minutes. Thank
Right.
you very much, all of you, for attending the conference.
Bye-bye.
Bye-bye. Hello. Now you can hear me, right? Okay. Sorry, I had some problems. Yeah, I was saying that yeah, thank you very much all for coming. Welcome, Professor Zachary, and thank you very much for being here. And we are very pleased to have you here in LoG, having a keynote. Just as a side note, before the keynote, we have oral presentations and also poster presentations. So just we have a long program ahead. Yeah, with no further ado, I will present Professor Zachary. So Professor Zachary is a research scientist at Meta, the FAIR team, and he is adjunct professor at the chemical engineering at CMU. He holds a PhD at MIT and a postdoc at Stanford. And the work that Professor Zachary does is an AI for chemistry and climate applications model to understand and design nanoscale interfaces, usually using machine learning. Some examples are computational methods for catalysis, as we can see, and machine learning models to predict their properties, or active learning methods to guide these systems. So with no further ado, I will leave the stage to Professor Zachary. So thank you very much.
Super, thanks so much for the invitation. And it's also fun to be here. I know a bunch of the students who worked with me at Carnegie Mellon and really appreciated the LoG conferences and the mentorship and other things for some of the projects. So today I wanted to talk about a couple of recent data sets and efforts that we've released openly that I think might be relevant, especially for people as they start to think about downstream applications of these really cool GNNs and other graph learning techniques that have been developed over the past couple of years. And specifically, I'm going to touch on two. One is OMAT24 and OCX24, and I'll get into exactly what we did there and how that might be useful for some of these energy challenges that are so important to the world today. So just a little bit of background on what FAIR and the FAIR chemistry team are for those who aren't super familiar with their work. So FAIR is fundamental AI research at Meta. Most of the things that you've probably seen from FAIR are things like Llama 123, vision models like Segment Anything, embodied AI, agents inside of robots and similar, and different language translation methods. One nice thing about being at FAIR is there's a general commitment to open and reproducible research. And so that's really helpful to work with the community and open as much as we can and move super fast. It's been really fun to see how much the community has helped on some of these open science challenges. One of the nice things about being at FAIR is obviously lots of GPUs for training large models, but we also have access to a lot of idle data centers for running simulations. And so that's sort of focused a lot of our efforts on how do we build the right computational data sets to help train the graph models and other fancy GNNs and things like that that we want to use for chemistry. And specifically, the chemistry team is about 15 people. We mostly work on open science things like catalysis and direct air capture and other material science problems. But more recently, some of our team has also helped internally with display materials for headsets and AR/VR applications. Okay, so really what I want to talk about today is focused on catalysis. And for those of you who it might have been a while since your last chemistry class, a catalyst is basically something you use in order to make a chemical transformation move faster. And this is specifically important if we want to try and electrify various processes around the world to address challenges in climate change. The most well-known process is you take renewable energy and you charge batteries, and that can help with grid applications or light EV, so small cars, super well established. We see that in our day-to-day all the time. But there's a ton of other uses of chemistry and materials, other sort of industrial applications that we also need to find ways to decarbonize. So things like heating of buildings. I'm sitting in a house. I think it has a natural gas system. I wish I could find ways of electrifying that. We have methods. Agriculture, ammonia takes a huge amount of energy across the world in order to make the fertilizer that we need. Trucks are harder to electrify. It's really hard to build an electric plane. Consumer products like plastics and industrial things like concrete and other applications, all of these also need to be electrified. And so there's not one way that we can do it, but there are a lot of chemical methods that we can use to produce these other things that are important. And so one way that we might do that is use renewable energy along with building blocks like CO2 or water. and then upcycle those into more valuable things like pure hydrogen or fuels for aviation or heavy-duty transportation or chemicals as precursors for plastics or concrete and steel for industry. And so I'm not going to go into a ton of detail on exactly the mechanisms and how we design a catalyst, but I'm happy to follow up afterwards if any of you have questions. I just want to get across that a lot of these challenges that we need to work on for sustainability are fundamentally catalyst problems, because these are all things that we need to know how to make. So as one example, for steam methane reforming, we want to make hydrogen, and that might be take methane and water and try to make CO2 and something like hydrogen. And a traditional process might be use oil as a process. And along with the hydrogen that you make, you might also make a bunch of CO2, which is maybe something that we want to try and avoid. Now, the equivalent electrochemical process is we might take water and electricity and split that into hydrogen gas and oxygen gas. And this is a much cleaner process in that it just has water as an input and hydrogen and oxygen as an output. Oxygen is all around us. But of course, we need to find a way of actually doing this fast. And so often we think about things like platinum surfaces in order to actually help us split this water and get the hydrogen. So that's what the catalyst is. For something like sustainable aviation fuel, if any of you have heard of that, basically, again, planes are really hard to electrify. So an alternative to trying to get batteries in planes is instead try and use renewable electricity and precursors like carbon monoxide or CO2, along with hydrogen that we've formed up here, in order to make higher hydrocarbons or alcohols, basically jet fuel. And again, this is basically a way of doing this more sustainably. That jet fuel can then be used inside of a plane. And the key is that it came from renewable sources and renewable electricity. So again, these are just a couple of applications. Now, when I actually try and discover a new catalyst for one of these processes, it's actually really hard, and there's several key steps along the way. So the first is you have to be able to identify potential catalyst materials. Like, what are the materials I'm going to consider? Are they surfaces or little nanoparticles or some porous material? There's not one right answer. People have thought about all of these over the past few decades in this field. The second is we need to find ways of prioritizing and screening them, basically which are the ones that are most worth our time. And finally, once we make some predictions here, we need ways of actually testing these in lab to say what are the best ones, and have we actually discovered something that can be used in a real industrial process. Now, most of the work in our group has been focused on this screening process, and I think we've made a lot of progress. I'm not going to go into a ton of detail, but I just want to highlight for anyone who hasn't seen the work. We've been running these open competitions and leaderboards for the machine learning community to introduce heterogeneous catalysis and why these things are important. If you go to opencatalyst.org, there's a live leaderboard. We see submissions every few months. It's been super fun to see the community propose new models for this space. I'll get into a little bit about the data sets, but the data sets are also really big. These are really interesting graph learning challenges. And it's also been fun because we've had both academic and industrial and other competitors basically submit models. So for example, Google DeepMind and Microsoft Research Asia and Tencent AI Lab have all contributed models that have ended up on this leaderboard, which has been super fun. We also run challenges at places like NeurIPS to basically keep the ideas fresh, and then periodically have new challenges to help the models keep on moving further. So the last one was in 2023. We're not going to have one in 2024, but I think we'll have one in 2025. Okay, so at the end of the day, we need data in order to train these large models. We want models that are large and generalizable and work across many, many different types of chemistry. Our group has released a bunch. So OC20 and OC22 are for catalysis and inorganic materials. ODAC is a data set of materials for direct air capture, basically taking CO2 out of the air and then trying to store that. We have a more recent model called, in dataset OMAT24 on inorganic materials. I'll talk a little bit more about that in detail. All of these are done with electronic structure calculations, basically really high fidelity physical simulations. There's hundreds of millions of examples. This basically makes it, again, a really interesting graph challenge. We don't just want graphs that work on small data sets, graph models. we want graph models that can scale to hundreds of millions of examples, and I think that's really helped push the field forward in terms of how fast and scalable these methods have to be. These were really expensive to compute, something like 1 billion CPU hours in total, and all of these have been open source for commercial or non-commercial uses. Okay, so today, again, I'm going to talk about two things. One is OMAT24, this data set to help us with this first task of identifying potential catalyst materials. And then later I'll talk about OCX24, which is basically a data set to combine experimental and computational catalyst discovery for the end. And I'm going to skip over this middle step only because we've had previous talks at LoG on screening catalysts and a bunch of other public demos and lectures and other things. So if you have questions about this middle step, feel free to follow up afterwards, and I'm happy to point you in the direction of more resources. So let's talk a little bit in detail about inorganic materials discovery. So for those of you who don't have a materials background, which I would expect is probably most, that's fine. A simplified view of the world is basically we have materials that are made 100% of zinc or 100% of copper. This is basically a little simple phase diagram of copper. And if we want to hypothesize a new material like zinc copper with a specific structural form, and this is a graph conference, so you can already see that these look sort of like graphs depending on how you define a bond inside of one of these systems. I hypothesize a structure, I calculate the energy with my favorite physical simulation, and now this forms a lower hull. This is basically a phase diagram, and what it says is anything that's up here is going to end up being more stable as a linear combination of pure copper and zinc copper. Now, if I come up with a new hypothesis for a different structure, so this is the same 50-50 zinc copper, but it has a different graph structure or a different crystal structure, and this one is lower energy. Now I have updated my hull to basically say this one is better than that one, and so I no longer need to consider this one is either metastable or unstable, and I'll get back to that in a second. And so this is now the best material at 50-50, and anything up here will decompose to a combination of zinc copper and 100% copper. Okay, if I hypothesize a better structure at a different composition, so 75% zinc, 25% copper, now this one gets used for the lower hull and gets updated. And this is basically the process of materials discovery. Now, of course, real life is not quite this simple. This is an oversimplified view of reality. And so a really common counterexample in material science is diamond versus graphite. So for any of you who has thought about jewelry, I'm sure you've heard the phrase diamonds are forever. That basically implies that if you have a diamond, that's the most stable thing and that will last forever. But both of these are 100% pure carbon. The graphite and the pencil is also 100% pure carbon. And if you do a calculation at room temperature pressure, sort of like all around us, actually what you find is that graphite is the more stable structure. And so what this says is, if you wait an infinite number of years, eventually the diamonds that we have in jewelry will eventually decompose into graphite. Now, in practice, this process is so slow that it's not something we need to worry about. I'm not going to go worry about the diamond in my wife's diamond ring basically decompose into graphite on our time scales. The barrier to go from this to this is really large, so it would take a really, really, really long time for that to happen. But nonetheless, if I waited a long enough amount of time, eventually I would form the most stable structure, which is graphite. Now, the other key here is that in practice, these phase diagrams are actually very dependent on the conditions that you test them at. And so if you look at really high temperatures and really high pressures, like you see in the mantle of the Earth, that's actually where diamonds are formed. And so at those specific conditions, actually diamonds are the most stable structure. And so in the mantle of the Earth, the diamonds that are formed will last forever. But as soon as you go to room temperature, again, bring them up to the surface, graphite becomes a more stable structure. And I'm just bringing up these examples just to help you understand what it means to discover an inorganic material, because this is super relevant to catalysis. And there's been so much excitement about inorganic materials discovery and graph networks that we need to keep these ideas in mind as we actually start to use these things in practice. Okay, so bringing this all together, basically what happens is we want to calculate formation energies. That's basically how stable is the material. We're going to use graph networks in order to do that. The materials that are most stable along this hull, we're going to call stable materials. Everything that is very close to this hull, we're going to call metastable. Maybe we can make it, maybe we can't. It's a little hard to know how fast it'll decompose. Diamond, I would lump into that category of room temperature and pressure. There's usually a little rule of thumb of about 0.1 EV per atom that people use to say how close is close for this hull. And then anything that is way higher energy than that, we would say that's probably unstable. Again, it doesn't mean you can't make it, but it means it's awfully unlikely and probably it's not going to show up in real life. And so when we propose a new material, either with some generative model or our favorite heuristic, we can classify based on these methods. So things up here will be unstable, things close to the hull will be metastable, and if you find a material that is way below the hull of the currently known materials, that's when you can say, okay, computationally, I have discovered a new material, and maybe that's when I should go and try and get my experimental friends to make it. And a couple of the metrics that the graph network community has used to try and track these things are things like the stability rate. If I hypothesize a bunch of new materials, what is the percentage that are actually stable, so below the hull, or perhaps stable, unique, and novel, that is, they are interesting and new, and no one has ever hypothesized them in the past. Okay, so let's talk a little bit about how to predict these formation energies. And again, this is one of the areas where graph networks have really changed the game and are being used in the day-to-day now. So we're really lucky to have these physical simulations that we can use as ground truth. They're not perfect, but they are very helpful in practice. Basically, we're trying to model all the electrons inside of one of these systems. We use computational chemistry codes, solve things like the Schrödinger equation, or use things like density functional theory to approximate and then solve that instead. And the really nice thing about these quantum chemistry codes is, although they're quite slow, they can run on classical computers. And if you have a large enough data center, you can run a lot of them in parallel. One of the things to keep in mind is that these simulations are really, really, really slow. So every time you want to calculate the property of a material, it's something like 100,000 CPU seconds per calculation. And if you look at most of the large generalizable GNNs that are used in the space today that are trained on millions or hundreds of millions of structures, most of those run on the timescale of about 1/10 of a GPU second per calculation. And so these are already about 1 million times faster. And again, I can't thank the graph learning community enough for helping with these tasks. It's been really remarkable how much progress has been made in the past few years in this space. Okay, so there's already some nice benchmarks by others in the field on whether or not models are useful for computational materials discovery. And so if you go to MapBench Discovery, this is basically organized by the Materials Project, which is a open science organization at Lawrence Berkeley National Lab. They've run this website. They've had this challenge up for, I think, about a year and a half now. Most of the top methods on this leaderboard are various types of graph networks. So MagNet, ChargeNet, MACE, 7net, Orb, Equiformer V2. I'll go into this one in a minute. All of these are various types of message passing or graph networks. Each of them has a really cool paper associated with them. MagNet and ChargeNet. MagNet came from UCSD, Shui-Ping Ong's group. ChargeNet came from Geert Ceder's group at Lawrence Berkeley National Lab. MACE is Gabrojani's model from University of Cambridge. 7net is a recent modification of NetQuip from a really well-known group in Korea. And Orb is a model that was developed by Orbital Materials, which is a startup in the space. So it's really cool to see a lot of recent progress. One of the metrics here is the mean absolute error for calculating the formation energy, the MAE. The units of this are electron volts per atom. And so 0.036 is pretty good already. If we go back and look at one of these hulls, I said, if you want to classify is something metastable or not, you need to be within about 0.1 EV per atom. So 0.1 is significantly larger than 0.036. And so already we're seeing a lot of progress. These models are getting pretty helpful for day-to-day discovery. All of these models that are listed here are trained on the same data set. So the same set of about 1.6 million structures that came from about 150,000 simulations where we were doing little local relaxations. And all of this training data came from the materials project. Again, it was a really, really well-known and very, very helpful open science effort in the materials community that's been running for over a decade now. Another thing to keep in mind with all of these is that when you're training on millions of structures, it's not surprising that the graph networks have also gotten quite large. And so if you look at some of the models from a few years ago, they were reasonably small, hundreds of thousands of parameters in these GNNs. But as you go to larger and larger systems, larger and larger data sets, again, not surprisingly, the models themselves have also gotten larger and deeper and more expressive. And so it's not uncommon to see tens of millions of parameters now, just to give you a sense of scale in these sort of systems. Now, of course, all of these are trained on the same training data set. And so another thing that you could ask is, what if we just add more training data? So I'm going to go into that in a second. Let's talk a little bit about what this model is. So EQV2 small DENS is basically a specific architecture, Acroformer V2, and DENS is a denoising strategy that we use for augmentation. So we actually didn't come up with this specific architecture. Acroformer V2 was developed in collaboration with Tess Schmidt's group at MIT. She's super well known in the equivariant GNN space. I don't want to go through all the details of this network. Basically, I just want to get across the input is a 3D graph. The output is something like the energy or the force. The force is a vector. There's usually a bunch of message passing steps in these systems where basically all the atoms are talking to all of their nearby neighbors, and we repeat that message passing step a few times. And then at the end, we have an output head that basically takes these learned representations from the GNN and then tries to predict the final properties of interest. There's a lot of work that's gone into how to make these things more scalable and more efficient. So for example, there's different convolution strategies, like ESCN was a model from the fair chemistry team that basically came up with a better, faster, more scalable convolution strategy that's used inside of Acroformer V2. And a lot of this work was done by Yilun Lao. He was a intern on the fair chemistry team 2 summers and 1 summer ago. And basically the V2 is basically taking the original Acroformer model from Tess's group, and then scaling it up to work at scale on hundreds of millions of examples. Now, the other thing I mentioned was this denoising strategy for augmentation. And this is basically coming from a limitation of most of the data sets that have been available. And so in the inorganic community, most of these simulations are local relaxations, local optimizations of a structure. You start with a hypothetical structure, you calculate the forces, and you move downhill to try and find a lower energy structure. And so the data themselves is usually not incredibly unique. A lot of those structures along the way are often very similar. So we've been thinking a little bit about how to help in this case. One opportunity is various types of denoising or dataset augmentation strategies. So one of them is called DENS. This is up on arXiv. It was basically an intern project from Yilun about not this past summer, but the summer before. Basically, given a structure, you basically try and modify it. And then the goal of the model in this augmentation system is basically, please tell me the original structure that had this specific force vector that I know is true. And so this augmentation basically gives an auxiliary system that allows us to train on other points nearby while still using the same original training data set. So this is basically an augmentation strategy. You can do it for a relaxed point too. If this thing is mostly relaxed, I can try and bump this quite a bit. And then again, the goal of the model afterwards is, please tell me the structure that has a very, very small force nearby, and hopefully it will map back to the original structure. Another thing that we could do is we could say, well, maybe this is just a problem with the underlying data set. Why don't we just try and build data sets that are far from equilibrium? If diversity is good, why don't we just go ahead and make data sets that are more diverse? And so that's specifically what we did with this OMAT24 dataset. So OMAT24 is massive. It's more than 100 million non-equilibrium structures. It's useful across many different application areas like catalysis and optics and electronics and many more. Inorganic materials are used in many, many, many different areas of material science. These were structures that were made by taking known stable structures and then using really high temperature sampling strategies to get really far from the original equilibrium. We also ran some short time scale molecular dynamics at 1,000 Kelvin or 3,000 Kelvin, really, really, really hot. or we try and rattle these a bunch in order to come up with, again, hypothetical other structures that we think are going to be useful for training the GNNs that we care about. This data set, again, is all open source. They're hosted on Hugging Face. The models that were trained on the data are also available on Hugging Face. If you use this larger data set, you can train much larger GNNs, and because of the additional training data, you can do quite a bit better. So if you just train on the original NP-Traj 1.6 million data set, I said that you could get an MAE of about 0.036 electron volts per atom. If you train a very similar model that's larger, 90 million parameters, because we have more data now, the total data set is about 100 million structures, you can get that down to about 0.02 electron volts per atom, which is starting to get really close to the underlying errors associated with DFT. That is, the models are so good that they are approximately as good as the noise in the underlying training data set itself, which is really amazing. So these models are openly available now. Anyone in the world can go ahead and use them. And now that this data set is open, I expect that we'll see some more models come up and beat Equiformer V2 as others in the community try and scale these things even further. Okay, another area that we can go is we can say, well, maybe we're limited by hypothetical materials. Why don't we work with generative AI to propose new structures? And so one example is motivated by Meta's MovieGen, which was released earlier this fall, basically a state-of-the-art movie and audio generation system. Our team has been working with some of the people behind MovieGen to apply various types of models to materials discovery. And these are also areas where a lot of others in the community have also had some really interesting progress. So one model that I'll talk about in a little bit more detail is we can fine-tune language models. That's a reasonable strategy. We can implement flow matching methods for these graph systems. That's what this GIF is coming from. Or we can try and combine the best of both worlds, and I'll talk a little bit about that. This flow LLM model is going to come out. It's already up on archive and will be at NeurIPS in just a couple of weeks in December. And the cool connection here is it's been really fun to see some of the ideas that have been developed at Meta for things like MovieGen, and specifically the audio generation system in MovieGen is a flow matching method developed by others in FAIR, like Ricky Chan and Yuri Lippman and others in the community. We can apply these same flow matching methods that were originally developed for audio generation, and we can apply them to materials. So it's been super fun to see this back and forth between the different communities. So let's talk a little bit about what some of these structure generation systems might look like. So on the left is one system that we worked on that was inspired by some work by Alana Sporoguzik at the University of Toronto. Nate Groover did this. Nate is a PhD student at NYU. He was interning with us, not last summer, but the summer beforehand. And basically what we did was we took Llama 2 models and fine-tuned them to generate these graph structures by saying, please give me XYZ structures and the shape of this system, the lattice cell. And the really fun thing was that at the time, we were able to show that these language models were competitive with some of the models that were available for structure generation, like CDVE. The source code for this is up on GitHub, and the paper was released at iClear this summer. Anurup Sriram and others in our group, Ben Kurt Miller, who also recently just joined, worked on another system, taking flow matching methods, like I said, from FAIR and applying them to materials generation. And they were able to show that they could do even better than a model that had come out in the intermediate time between these two called DiffCSP. And basically what this model is doing is basically deforming this thing to find an even better crystal structure given a hypothesis, which is the initial one. And if you look at the original structure, most of you probably haven't done enough material science to see that the original ones are not very realistic, but by the end, they're starting to look fairly ordered, and it looks pretty close to maybe an oxide system. These little red atoms are probably oxygen atoms, and these blue ones are probably some sort of metal. One of the really interesting observations that we saw was also that this chemistry language model seemed to work really well for telling us what types of materials to make. And this flow matching method seemed to do a really good job of putting the atoms in the right place. And so a more recent model we call Flow LLM basically combines these two for best of both worlds. We basically use a language model to tell us what sort of structures we should be trying to make, like what's the composition or maybe an initial guess on the crystal structure. And then once we have an initial guess, we use flow matching with this Riemannian flow matching method that I talked about previously to basically come up with a denoise structure that is even more stable and better than the original initial guess. And so again, this is up at on archive now. I think the source code is also up or will be shortly, and it will be presented at NeurIPS in a couple of weeks. Okay, and again, one of the really fun things about this area right now is that there's not one right method for generating graphs for this system. These ideas and strategies are synergistic, and that means that we're going to see probably a lot of progress in the next couple of years as people mix and match these different methods. So if you take this crystal generation, this LLM-based method, and the slow matching one, and combine them, you get a method that is way better at predicting stable structures than either of these alone. And again, just from a opportunity for methodological improvements in the space, I think it just says the field is wide open. And it also says that all the work that's going into other methods for generative AI in language and image and video, a lot of these are probably going to be applicable to graph generation as well. Okay, so I want to switch gears a little bit and talk a little bit about how we make data sets and test materials like Catalysis in the lab. And specifically, we have this OCX24 data set that we recently released that I think will help the community make some progress. So OCX24 is basically Open Catalyst 2024. The X stands for experimental. It's a combined computational experimental data set that we think is going to be useful to help us make AI-driven discovery and catalysis even more meaningful. And I would say the data set and the methods that we released as part of this paper are relatively simple. And so I think there's going to be a lot of low-hanging fruit and progress from the external community and making these even better. And I hope that someone on this call comes up with an even better strategy than what we came up with. Okay, so in summary, basically what this data set is it's a computational data set of little molecules sitting on surfaces that we think are correlated with experimental catalysis. They were calculated for about 19,000 stable and metastable materials, and I'll talk about where we got those from. With each of these materials, we formed many, many different hypothetical catalyst surfaces and placed these little adsorbates on them. And so in total, we used some of the state-of-the-art graph neural networks that we developed as part of the Open Catalyst project to run hundreds of millions of simulations, run DFT calculations on the best of those, and then that forms the computational part of this data set. So these are things that we can calculate with simulations that we think are going to be relevant to the final experimental testing. On the experimental side, I'm going to go through in a little bit more detail. Basically, we have two different synthesis techniques, lots of characterization to help us identify what materials we made, and a testing platform so that we can actually say, what is this catalyst doing? So this data set was done for two different types of chemical reactions, both of which I touched on at the beginning of this presentation. So one is hydrogen evolution. Given water and electricity, split it to make hydrogen gas and oxygen gas. This is useful for making, again, hydrogen as an energy source for a hydrogen fuel cell. And the second is the CO2 reduction reaction. CO2 plus hydrogen plus electricity makes fuels or higher hydrocarbons or plastic precursors. So, how do we know which materials are actually going to be stable as a catalyst? So if we go to an open database like the Materials Project, there are about 150,000 structures. About 60,000 of those have actually been synthesized experimentally. Most of those are not actually going to be stable when you actually put them in water and you apply a potential and try to make this thing into a real catalyst. And so if you screen for stability, basically you find, even though we know about 150,000 materials, actually under reaction conditions, when this thing is actually happening, only about 6,000 will stick around for a long time. The other 149,000 will probably decompose under those conditions. So 6,000 is a good starting point. but we also wanted to try and expand this number a little bit. We wanted even more possibilities. And so in addition to the materials project, we also considered 2 other data sets, Alexandria and OQMD. And in total, if you take all 3 of these together and you screen for ones that are going to be stable, again, under these conditions, you find about 19,000 materials that are probably going to be okay to actually test if you can synthesize them and get them into a real catalytic reactor. Okay, so what do we want to do? The dream would be basically we have 19,000 materials, we order a whole bunch of those, make a whole bunch, and then test them all, and then release an experimental data set. Unfortunately, real life and real catalysis is quite a bit more complicated than that. So what do we actually have to do? So first, we had to try and figure out which of those 19,000 we actually wanted to make, either with some screening strategy or some sampling strategy ahead of time. Next, we had to go and work with a bunch of experimental partners to try and find synthesis techniques to actually make the materials that we care about. Then we had to find a way to get those things that we made in nanoparticle form to actually stick to the electrode in the membrane so that we could use them in a catalytic reactor. And often we had to repeat this process a few times. So not every way of making the materials is compatible with how we were getting them to actually stick to the electrode. And finally, even once you get them on the electrode and you run the reaction, you have to characterize the materials to make sure that you actually made what you wanted to make. So if I came up with a hypothetical structure, I don't want to test something random. I actually want to test the structure so that I know that I can match computational experimental data at the same time. Often, I don't actually make what I was hoping to make, and so I might have to go back and tune or change or come up with a new synthesis strategy and then repeat this whole process again. And finally, on the timescale of years, we were able to make a couple of hundred of examples of these materials. And so these couple of hundred are the ones that were released in OCS 24, and these are the ones that were actually tested at scale. So what this process looks like is basically there's 2 strategies, chemical reduction and spark ablation. Chemical reduction is a technique that was done at the University of Toronto. Spark ablation is a method from a startup called VS Particle. Again, we had characterization and lots of these electrolyzers in parallel to basically try and test these things. This is a picture of a chemical reduction robot from a ChemSpeed system. This is a VS Particle machine that's doing the spark ablation to make these arbitrary nanoparticles in these little film form. And finally, this is a picture of this testing apparatus to basically say, how good are these at actually making real catalysts and turning CO2 into something more valuable? And the sort of data that we get out looks something like this. So at 3 different applied voltages, different conditions, how much energy are we putting into the system? These catalysts will make varying amounts of hydrogen or methane or CO or ethylene or other chemicals. So for example, for this copper nanoparticle system, at low current voltages, it makes mostly CO, and at very high applied potentials, it makes mostly hydrogen. And depending on the synthesis strategy, we get qualitatively similar results, but not quantitatively the same. So for example, chemical reduction versus spark ablation, you get some small differences in how much CO you make at intermediate current densities. So this is really just to give you an idea of what does this data set look like, what are the outputs, what are we trying to fit? And these are all things that we will want to correlate with the graph networks and their predictions on the catalyst side. Okay. In total, we made about 500 materials. 200 of those were clean enough and deduplicated for testing. This is an order of magnitude larger than any other data set that we're aware of for these sorts of electrochemical conditions at high current density that have been released openly. You can see that some areas are much denser than others. So we have a lot of zinc and silver and copper and gold systems. Some areas are harder. There's not that many materials that are stable that have gallium or indium. And so these are a little bit less common. Just to give you an idea of what the distribution of this data set looks like. And one really cool example, again, just going back to what are we using these graph networks for, I want to highlight some of the results for the hydrogen evolution reaction. And so I've said this a couple of times, but basically hydrogen evolution reaction, HER, is basically water plus electricity forming hydrogen gas and oxygen gas. And if you just take really cheap but simple descriptors based on the composition of the catalyst, so like what is the atomic mass of the elements and their radii and electronegativity, you can fit the experimental data on the y-axis, the predicted voltage, to the experimental voltage, and you can get a reasonable parity plot. So an MAE of about 0.09. I would say that's not the most beautiful linear regression and set of residuals fit that I've ever seen, but nonetheless, the R squared is about 0.5. That's somewhat reasonable in this space. If you then go and predict all the other materials that are hypothetically possible, you see that there's a whole bunch of materials that are predicted to be way better than the ones that we tested in gray. And specifically, the material that is most well known for this reaction, platinum, which was not included in our data set, shows up as a star. Basically, what this model is saying is there should be a whole bunch of materials that are better than platinum, which is hypothetically exciting. Now, what was really exciting to us is that if instead of using these really simple composition features, instead we used features that came from these graph networks trained on the Open Catalyst project, and so these are things like hydrogen or OH absorption energies feeding into the same linear model, we get a fit that looks qualitatively very similar. The parity plot is very similar. R squared is also about 0.5, 0.6. MAE is about the same. But when it comes time to make predictions, this is a much more physically meaningful and realistic graph. It has this characteristic volcano shape that shows up in the catalyst literature. Basically, what it says is that there's a sweet spot here that catalysts like platinum happen to lie at. And this platinum catalyst is, in this model, predicted to be one of the best known materials. And this actually matches what happens in real life. There's a couple of other materials here that we think are a little bit better that we're trying to test. But we're not making these predictions that there's going to be ones that are way better. And if you actually tested most of these materials that came out of this original model, I think you would find that almost all of these are actually not better than platinum in practice. And so this is basically a long-winded way of saying that we were really happy that some of the models and GNNs that were developed and by the academic community for the Open Catalyst project seem to have better extrapolation and more physically meaningful outcomes than if we had just used really naive descriptors at the beginning of this project. Okay, so in summary, I hope I was able to convey that this is a super exciting time to be at the interface of AI and chemistry and material science. The graph learning community has just made a ton of progress in the past few years. Some of these models are really helpful now. We're starting to think more about downstream applications and all of the other things that have to go right for materials discovery in this space. This has really been a community effort. It's not any one group. It's been this sort of competition and back and forth and open leaderboards that have driven a lot of this progress, which has been really fun to see. Another fun thing has been models that were developed for the Open Catalyst project leaderboard also seem to be correlated with models that are state-of-the-art for other areas like inorganic materials discovery. And so I showed that basically Aquaformer V2, a model that is currently state-of-the-art for catalysts, also can be made state-of-the-art for inorganic materials. We've released a new data set for the community, OMAT24, that I think will drive a lot of progress in the next year or two to come up with even better models. And finally, I touched on some emerging work on high throughput experimental data sets. These are hard. Finding materials and testing them across many, many different types of elements and compositions is really complicated. We've released the first data set from our group in this space, OCX24. I expect there'll be others from the community. I think we're really at the beginning of this journey, and I think there's a lot of opportunity for graph networks to help in this area as well, either by helping with the original sort of synthetic simulation data sets and making those more accurate, or perhaps directly helping us predict experimental and computational results and making the bridge together. Finally, I just want to say everything I talked about today was 100% a team effort. It's been awesome to see all the collaborators work together to enable these new data sets and systems. So we have a large group at FAIR. We also have really close collaborators at Carnegie Mellon, like John Kitchen, collaborators at the University of Toronto, like Ted Sargent, and others. And finally, I didn't touch much on the direct air capture work, but I mentioned it. That's mostly been in collaboration with Georgia Tech. We've also had some recent interns who have contributed to a lot of these projects. So with that, I'll stop there. Happy to take any questions. And if I don't address anything and you have any questions afterwards, feel free to shoot me an email or follow up on our GitHub page and post issues if you see anything interesting. Thanks so much.
Thanks so much, Zachary. Thanks so much. It has been very insightful, very exciting. I've learned a lot about how to use it. I think you have conveyed very properly how like all the methods based on graphs or they help to speed up both the process and they are also very fast compared to other computational methods. So I think it's very interesting and very insightful. If anyone wants to ask questions, we have the chat open. I think there is one question, also Slack and anything else. Rafael Artinano asked you a question, Professor Zachary. Would be interesting to predict the parasite processes within the material discovery?
Yeah, I think what you're asking, but correct me if I'm wrong, is basically if you're trying to make these things, you might make a bunch of other things by accident that may be parasitic in that you were trying to make something, but there's some other process that you don't want to happen. And that really gets to real life is often not about the thermodynamics, which is this really simplified view of inorganic materials that I was showing about, talking about before. I'm just going back here. But actually, it's about the kinetics of these different processes that are all happening at the same time. And often the one that's the fastest wins. So the reason I and the rest of the field have focused on the thermodynamic sort of view of the world of just what is the most stable is it is way simpler and it was easier to make models and data sets for those challenges. But now that we have these, we need to go the next step and think about these kinetic processes in parallel that you're talking about. And I think that's where the community is heading. So using the graph networks that have been developed to say, what is the rate of reaction to go from A to B to C, and what are all the other processes? That's exactly what you're going to have to do to get models that fit the experimental data even better than the current ones. So we're just at the beginning stages of that. One of the reasons there's been so little work in that area is just these simulations were so expensive and so slow and so annoying to converge in the past. We just weren't asking the more physically meaningful questions that we were hoping to do. But now that we have these GNNs, I think we can really move very fast.
Yeah, great answer. He says thanks as well. Yeah, also Shaitanya had a question about, that's also a question that came to my mind when you were showing the table about the data sets and architectures. How responsible are, in terms of improving the performance of the field, the data sets and the architectures? So the exact question is, how do you weight the data sets or the architectures in terms of importance in pushing the frontiers in material discovery? Like, yeah.
Yeah, that's a great question. So the short answer is I think all of these have to happen in parallel and have happened in parallel. And so what I mean by that is if we had gone back 5 years and we had said, okay, the only thing we're going to do is methods development for GNNs, I think we would have made progress, but we wouldn't necessarily have come up with architectures that were going to scale to hundreds of millions of examples. And so the ones that are the best right now in these really large leaderboards are also the ones that are simultaneously expressive and fast to scale. And that's important in practice. On the flip side, if we had only done data sets and we had never done any work on the GNN side, the original GNNs 5 years ago in the material space, like CGCNN, They were so cool to see and were way ahead of their time in terms of like how they were thinking about the world, but they were clearly not expressive enough to really get at these sort of kinetic questions. And if you move atoms a little bit, what are the properties going to be? And so I think, again, it has to be both at the same time. There's a limit to how far we can push the data generation side. So 1 billion hours of compute for all these different data sets and hundreds of millions of examples. We can continue to do that for a while, but like realistically, we're not going to get 100 times more data here. There's sort of like an upper limit on what's possible. So we either have to get smarter about how we generate the data and choose new structures. Maybe that'll be more active learning or other methods of selecting points that are the most meaningful, or it could be higher fidelity simulations. These are approximations of reality. They aren't perfect. Probably there will be smaller data sets of really, really accurate calculations that will come next. So there's still a lot of work on the data set side as well. And I also just want to convey, if you look at the Open Catalyst project leaderboard, we've seen a steady stream of new model architectures every few months. I think there's going to be another one that'll show up pretty soon on the leaderboard. I hope that that continues for a while. Every time another one comes from either us or the community, it gets me really excited. I don't know what's going to happen next year, in all honesty. Like, obviously, we're trying some random experiments to see other cool things that we think might be interesting. But again, a lot of the advances have come from the academic community, and we've been surprised. So I really hope someone on this call comes up with the next architecture next year.
Yeah, yeah, definitely, definitely. So before we finish, Samuel asked, what do you see as the biggest challenge facing the field over the next few years?
Yeah, I think that's there's so many things that have to happen here. So I would say maybe the most important is really on the experimental data set side. And so going through all this work, right, we came up with systems that were, I would say, quite industrially relevant. Like the way that we were testing these catalyst materials was maybe not exactly the thing that you would use at full scale in industry, but they were pretty close to the current densities that you would see. They were pretty meaningful. We did hundreds of examples here, and I showed you these are definitely not perfect models that have been developed so far. There's a lot of scatter here. And so I think there's a ton of room to make these data sets even bigger. And that's going to be important if we want more data-driven methods in the actual experimental discovery process. And so that's not, I would say, not wildly creative on my part. There's a ton of people in the community who are pushing on this. That could be high throughput systems, but if you do high throughput, you also need to make sure it's still industrially relevant. It could be automated robotic systems to basically do these things faster. It could be other ways of testing. Probably it's going to be a combination of all of the above. But I think that's going to be really important to make these experimental discovery processes statistically significant. If you look at the way most of it's been done in the past, it's been individual papers on individual compositions a few at a time, and it's really hard to make progress in data-driven methods when that's the state of the art. So these are all hard problems. To be honest, it's not clear if it's going to happen in 1 or 2 years or 2 or 5 years or 5 or 10 years, but that's clearly a direction that the field has to go.
Yeah, thank you very much. I think we are running out of time, so I would like to thank you again. I think you transmitted all the excitement about the field. It has been a very insightful talk. So thanks, Professor Zachary.
Thanks so much for the invitation.
Thanks, our pleasure. And we are gonna move to the oral, so I will pass the mic to Yambang. Hey, Yambang.
Hey guys, yes, I'm here.
Yeah, we can hear you.
I'm just trying to make Steve as co-host as well. So, all right, so I guess we will just begin. because we are a bit behind schedule. All right, guys. So welcome. This is the second oral presentation, and my name is Yanbang. I'm from Cornell University. I'll be today's host for the presentation section. And without further ado, let's welcome our first speaker. I think it's Christopher Blöcker, who is currently a postdoc at the University of Würzburg in Germany. And I think he will be presenting to us comparing hierarchical network partitions based on relative entropy. So Christopher, are you here?
Have you made him co-host?
Yeah, I just made.
All right. Yeah.
Yes, I'm here, and now I can also say it.
Sorry.
No worries.
Yeah, whenever you're ready.
Yeah. I'm currently at the local meetup in Germany, and in case you hear some noise in the background, then you know what's going on. It's a poster session going on at the moment, and some band is rehearsing for a little bit of music later today. But okay, let's go with the presentation. I'm going to talk about comparing hierarchical network partitions based on relative entropy, which is a work together with Ingo Scholtes. So just to start with the too long didn't listen version. So we can partition networks in many different ways, which means that we often compare partitions. And the problem that we see with common partition similarity scores is that they ignore link patterns, measures like the Jaccard index and variance based on mutual information. So what we do is we propose a measure that we call flow divergence, which is a link-aware partition similarity score, and based on the combination of describing random walks and the ideas behind the Kullbach-Eichler divergence. So comparing partitions, let's say we have some items, and they are partitioned in some certain way. Let's say this is our reference partition, and now we have another way of partitioning them. Let's say like this. Then we can take, for example, the Jaccard index to compute how similar are those two partitions of the same elements. And basically what happens here is that we look at all the elements that are blue, and we're checking how many of those agree. In this case, 2 out of 4 that are blue would agree between the two partitions. And to compare those, go through the colors and check between partition A and B. For each color, how well do they agree? And we might have to search through all the different groups because the colors might be flipped somehow in one of the partitions. Here, the Jaccard index will tell us, well, the agreement between B and A is 1/2. And we can also come up with other ways of partitioning the same elements where the Jaccard index will tell us that the agreement is the same. So these two partitions, C and D, have the same agreement with A as B has. And similar things would happen for mutual information-based measures, essentially because they are considering set overlaps. But we're interested in comparing network partitions. So if I take these partitions from before and draw them as a network and interpret what we have as communities in this network, now we would commonly just use the same measure again, the Jaccard index, to compare how well does B align with this reference A, how well does C align, how well does D align, and the Jaccard index would tell us that, well, they all agree to the same extent. And then you should ask the question, well, but what about the links? Because if we consider these partitions as community structures, then there should be some difference between C and D. For B and C, we can see, okay, there is a lot of symmetry, so they are probably the same, but there should be a distinction between D and the other ones. So our idea is here to combine ideas behind the KL divergence and random walks on networks. So the KL divergence, I'm sure that many of you have heard what it is and know it, but just to recap, let's say we have a set X of some letters, A, B, C, D, E, and they appear according to P. And let's say now we have a sequence of those letters coming from some source, and we want to describe the sequence. What we can do is we can design a Huffman code based on the frequencies and use one code word per symbol. How many bits do we need to use per symbol in theory? Well, that is given by the entropy of this distribution P. In this case, 1.96 bits. Now, let's say we have an estimate of P that is Q, perhaps based on the frequency of the symbols that we have observed. And assuming that these are the true frequencies with which the symbols appear, we would design a different code to encode the sequence. Would then encode it like this, and would get an entropy of 2.17. What now the KL divergence does is it tells us if we use a code that is optimized for Q to describe symbols that are distributed according to P, how many bits extra are we going to pay for this? So what we're going to pay then is the entropy of P plus the KL divergence of Q to P, 0.15 bits. And that is different from the difference between the two entropies. Okay, so the KL divergence tells us how much do we pay extra for using the wrong code, so to say, by assuming a different distribution than the correct one. Now let's take a look at random walks. Now we have a graph, we take a random walk on it, and now it's this random walk that generates a sequence of symbols for us. And these symbols are now the nodes. We can describe the sequence of nodes in a similar way by assigning code words to the nodes and then using one code word per step of the random walker to say where the random walker is. The description length for that, in this case, where we don't have communities, is the entropy over the node's visit rates. So we actually don't need to simulate a random walk or assign code words. That is just for illustration. What we're actually interested in are the visit rates for the nodes, which in undirected graphs, we can compute them directly. Otherwise, we might compute them with a power iteration, perhaps using PageRank or other means of calculating a stationary distribution. And if we then combine these two equations, 1 and 2, we can essentially rewrite the entropy in the shape that looks like a random walk. We have the random walker at a node U with probability PU, and then it will take steps from node U to node V with a certain probability, TUV, and the number of bits that we need to describe the step is log2 of PV if we don't have communities. But we are actually interested in communities because we want to compare network partitions. So this cost in bits, that is log2 of PV, we're going to replace it by something that we call here S of MUV. So S is simply a function that tells us, given a partition M, stepping from U to V, what is the rate at which the random walker does this, and log2 of that will give us the number of bits that we need. And we're going to use the map equation, which is an information theoretic objective function for community detection, to obtain such an S that tells us how much do those steps cost. So let's get back to this network. Now, if we look at it, we see there are 3 communities. What we can do then for obtaining a more efficient description of a random walk is that we can assign code words that are unique within communities. But now we need to add also module boundaries or community boundaries with specific code words to enter and to exit the communities so that it becomes uniquely decodable, and we can communicate in which community are we. And when I say I visit the node that has the name 00, we know by the context of the community where we're in which of those ones I mean. If we then take the same random walk again to encode the same sequence, we would do it with these code words where the colors indicate from which module the code words come. And the code length, so the number of bits that we need to use per step, is given by the map equation, which is shown here to the right. Essentially, it's a combination of a weighted combination of entropies. So in the front, we have the entropy of switching between modules, and Q is the rate at which we need to use this code word. And then the sum contains one entropy term for each of the modules and a weighting factor for that corresponds to the fraction of time that the random walker spends in the module. If we were interested in detecting communities, we would minimize this by searching through all possible assignments of nodes to communities and select the one that gives us the shortest description. One nice property of the map equation is that we can actually rewrite it, that it looks like the random walk description that we saw on the previous slide. So we have a random walker at a node U. It takes a transition from U to V. And the cost or the rate at which the random walker does this is now given by mapsim, which I'll show it in a moment, but it says that based on these modules, what is the rate of a random walker given these modules stepping from U to V? Again, we don't need to simulate an actual random walk. And we can, now that we have these communities, visualize the coding structure of the network as a tree annotated with code words. But again, we don't actually need code words. We're interested in the stationary node visit rates and the transition rates between modules. Mapsim basically looks at this coding structure and says, okay, if I have this coding structure given, or these transition and visit rates for the random walker that are normalized per module, what is the rate that the random walker goes, let's say, from the green module to node 1, or is in the green module and goes to node 10, and so on. Now, the partition dissimilarity score that we propose, we call it flow divergence, as I mentioned, is based on the combination of the KL divergence and describing random walks on networks. And the idea is that we want to measure how many extra bits do we need to describe a random walk if we use, so to say, an estimate B of the network's, so to say, true partition A. So we designate again one partition as the true one, and then look at another one that we want to compare to it. So going back to this example from the beginning, we take the reference partition to the left, and we'll look at this coding schema, that coding scheme that is derived from that, and use the one to the right to compare. So essentially here on the left, we have again the KL divergence. On the right side, the map equation rewritten to the shape of a random walk. We combine those to kind of look like a combination of KL divergence and the map equation to answer the question, how many bits do we need extra? But this is not quite what we want, because if we now substitute in the definition, then we will see that we only get a difference between two partition quality scores. So what we're actually going to do, there's a small difference here. We are using the partition-dependent transition rates, which are derived from this coding scheme that I have drawn as a tree, like this one. And we basically simply normalize them properly. Now you might look at this and see like, oh my God, we have a double sum over the nodes. That doesn't look very efficient. But it actually turns out that because of the regularities and redundancies in this coding structure, we only need to consider m times n many pairs of communities and nodes. And typically there are much fewer communities than nodes. So we don't need to consider the full m times n, so n squared many pairs of nodes, because of the redundancies in the community structure. So if we now look at the initial example again, if we use the map equation to measure which partition is best, then we see the reference partition A is best. Next, B and C, they have the same code length of 3.73 bits. And D is the worst in this case, 4.47 bits. Now, when we use our partition dissimilarity score to compare pairs of partitions, we see that in the first row here in the table, actually, well, A is completely identical to A. B and C have the same dissimilarity, and D is a somewhat, or about a bit, not quite a bit, but half a bit maybe, more similar to A than B and C. And the reason for that is that the overlap between A and D is in the nodes with a higher degree. So the nodes that have a higher visit rate, where the random walker has a higher probability of being there, so that the resulting coding structure for describing the random walk changes less compared to partitions B and C. So here we see that only because a partition has a better quality score, in this case B and C, than D, they don't need to be more similar to the reference partition. And we can also do the same thing with hierarchical partitions. Here we have two partitions where one has just single level of communities, the other one has two levels of communities. There we can look again at those coding schemes and make the comparisons. And because I think I'm running out of time, I would like to conclude. So our motivation was that communities are based on link patterns, but common partition similarity scores, they typically ignore links because they weren't designed for this application. And our solution is that we combine the ideas behind describing random walks and the KL divergence to develop a link-aware partition similarity score, which is asymmetric. It does not require matching of communities between partitions, like we had in the Jacquard index that we need to match and find the best match between two partitions. And we can naturally compare hierarchical partitions because this is based on random walks in the coding scheme that allows us to describe transitions between any pairs of nodes. So thank you very much for your attention.
All right, so thank you so much, Christopher. So we still have a few minutes for Q&A. I think there is one on our Zoom, which is how does these differ from MetaPath prior-based approaches?
I'm afraid I'm not aware of that approach, so I might not be able to answer that question. Could you say again? I think I cannot see the. There's the chat, perhaps. No, I don't see the message in the chat.
You can see message. So it's the Q&A function on Zoom.
Oh, okay.
And okay, so I think it's asked by VK. And if you are here, can you think I can make you co-host to let you clarify, I guess. VK. Yes, if you would like, I think you can now use your microphone to clarify your question if you want. So how does this differ from MetaPath prior-based approaches? I think the question is.
Is it
okay?
MetaPath prior. Okay, since I'm not familiar with it, I'm gonna look it up and see, and perhaps if the one who asked the question is still interested, perhaps just drop me an email and we can discuss it offline, because right now I believe I cannot answer the question, unfortunately.
I guess from my understanding, MetaPath-based approaches is just like a more fine-grained version of your random walk-based ones, because MetaPath have stipulated schemes for those walks. But random walks, you don't really require the node types of each step in your random walk, I guess. So that's I guess, my understanding. Okay, cool. So do we have any more questions coming up? Guess we can still take one or two. All right, so. Guess if there's no question at this point, I do have a question. So I think, so first, I guess it's a comment. I think it's a very nicely intuitive idea to kind of use the random walk to kind of encode the structures of the communities. And also you use PageRank to kind of very efficiently compute the blending probabilities of random walks, which makes your basically the matrix to be quite efficient and computable. So I think that's very nice. And I guess one question I would have is about like, have you tried your measure on some of the real world data sets and test some of the community detection algorithms performance based on your matrix? And what kind of insights can we possibly get from doing that?
Well, I have looked a little bit into what happens if we have limited data. And the thing that usually happens is that community detection algorithms, they say that, okay, now it's easier to find communities, so there's missing data. So it's kind of like, okay, now we overfit. But as this happens, the flow divergence actually becomes larger. So what you might think you gain in compressibility, it's actually you're getting further and further away from the, let's say, like the true partition, if we can say that we have something like that.
All right, thanks. So I guess we have another question from Rafael Artinello. I think the comment is that one question would be interesting to check arbitrary lengths. I'm not sure if that's clear enough for you to answer.
Arbitrary lengths. I'm not sure if that perhaps relates to the random walks. So I'm actually considering the statistics of random walks in the limit. So there's not a fixed length, if that was perhaps, I didn't make that clear enough in the presentation.
Okay, thanks. So I guess with that, I guess we will just conclude the first presentation by Christopher. Thank you very much for your time. And that's an excellent talk. We will move on to our second presentation by, I think it's going to be presented by Antonin Joly, who is currently a PhD student at CNRS in France. So I think he will be presenting graph coarsening with message passing guarantees. So I'll now transfer the host, yes, the co-host to Antonin. And
oh, hi everyone. Can you hear me?
I can hear you okay.
Okay, fine. Okay, so hi everyone, I'm Antonin Joly and I'm here to present our work, graph coarsening with message passing guarantees, which has been accepted this year to NeurIPS. So in the recent years, graph neural networks struggle with large graphs, such those used in recommender system. One of the techniques employed to solve this issue is to use graph coarsening, and consists in reducing the size of the graph by mapping the node of the original graph to some coarse node in a coarsened graph. But we might wonder if training a GNN on a coarsened graph is probably close to training it on the original graph. So I will begin by introducing some notation on graph coarsening. I will use the notation of Andreas Lucas with some generalization. So graph coarsening is defined on an original graph and produce a coarsened graph GC and a coarsened matrix Q. The coarsening matrix Q defines the mapping from the original graph to the coarsened graph. If Qij is non-zero, has a non-zero value, it means that the node J of the original graph is mapped to the node I in the coarsened graph. Then we can define for all signal living in the original graph, such a feature, we can define the coarsened signal Xc with the coarsening matrix Q. And we can define the uplifted signal in the original dimension, the reconstructed signal tilde X. To define this uplifted signal, we use the lifting matrix Q+, which is the Moon-Penrose pseudo-inverse of the matrix Q. Then we can define the projection operator P, which is the coarsen and then lift operator. Now I would like to introduce a very classical spectral guarantee introduced by Lucas, by Andreas Lucas. It is named the restricted spectral approximation constant. It is the sum over all the signal living in the low frequency of the Laplacian of the signal and the difference between the signal and the reconstructed signal with the projection operator P. It can be seen as a quality measure for the coarsening, and many classical coarsening algorithms aim to minimize this spectral guarantee. Now we just briefly recall that GNN relies on neighbor propagation. The node features at a step L depends of the node feature at the previous step, and the multiplication by a so-called propagation matrix, which we denote it as. It can be the adjacency with different kind of normalization. But we might wonder, what is the best choice of propagation matrix on the Coarsening graph? So we can think to use the same normalization as in the original graph, or a weighted version proposed by Wang. But with these classical choices, spectral guarantees on the coarsening does not lead to message passing guarantees. And to solve that issue, we propose a new propagation matrix on the coarsening graph, which depends on the coarsening matrix and the uplifting matrix. You can remark that even if S is symmetric, our propagation matrix is oriented. You can see on a very toy example with the propagation matrix being the adjacency. You can see the original graph, the Coarsen graph, and then our propagation matrix, which has the same weights as the Coarsen adjacency, but you divide it by the size of the source supernodes. So it is a weighted propagation, which is independent of any coarsening algorithm used to produce it. With this new propagation matrix, we're able to bound the difference between all signal propagated in the original graph and the Coarsen signal propagated in the Coarsen graph without propagation matrix and then uplifted in the original dimension. The key point is that these upper bounds depend of a spectral guarantee, namely the RSA constant. That means that if we have a good coarsening algorithm with strong spectral guarantees, we will have a better bound, we will have a better reconstructed signal. To have this theorem, we make additional assumptions that are easily verified for most of the propagation matrix and Laplacian used. So here you can see some example, some illustration of this theorem. So it is the same plot, one with a log, one with a log scale and one with a linear scale. So you can see our bound, our theoretical bound in dot lines. So you can see it is very tight for small coarsening ratio. For small coarsening ratio, our propagation matrix is the only one below that bound. So it emphasizes how good the bound is for small coarsening ratio. So we compare it to like the two classical choice I have introduced before, so the same normalization and the weighted version. And we also compared the two symmetric version of our coarsening matrix, one with a coarsening matrix Q and one with the uplifting matrix Q+. So if we make some additional assumption about the loss function or the activation function, we're able to extend the propagation theorem to GNN training and to bound the loss of the GNN trained on the Coarsen graph and the loss of the GNN trained on the original graph. This upper bound still depends on the RSA constant, but the activation function assumption is quite strong. And for now, it's only verified for the activation function being the identity. So thus the SGC network simplified graph convolution. But additional work could be to extend this assumption to other activation function and then other GNN. So to illustrate this example, we conducted several GNN training on the well-known Cora and Sightseer dataset and the 100 times larger graph Reddit for node classification. So you can see that for the SGC networks, which verifies all our assumptions, the benefits of our coarsening matrix are more evident, and it outperforms all the other choices of propagation matrix. When we relax the assumption on the activation function, and we have results with a classical GCN, we can see that our results are a bit blurred, and our propagation matrix is still competitive, especially for high coarsening ratio, but some other choices might be a good idea, such the weighted version of Wang. To conclude, I would say that in this work, we directly link the spectral guarantees and propose a new propagation matrix to have like message passing guarantees and then GNN training guarantees on the Coarsening graph. This is only the case for this Coarsening matrix, which has the particularity to be oriented, but doesn't and is independent of any Coarsening algorithm used to produce it. Future works could be to explore the activation function assumption, especially because it is for now quite a strong assumption to have the commutation property. But other works could also include additional assumptions we made. I thank you for your attention. If you have any question, I would be glad to answer it. And you can also see me at the poster session if you have any other question.
All right, so thanks so much for your exciting talk. And I think we still have quite a few minutes for questions.
Yes.
So I guess we can wait a little while for people to type in questions if they have. I guess I have a quick question. Like, can you elaborate a bit on the just on this page, like when you use GC and Con instead of SGC to run the experiments?
Yeah. We
can see that the other coarsening method in your baseline SC diag actually yields better result. I was probably a little bit lost. Can you elaborate a bit on like why that happens and what exact insight we can get from that?
Do you mean why do we have like less good results with GCN compared to SGC?
Yes. When the coarsening method is not your proposed one, but the one in baseline.
Oh yeah, this is mainly because we provide our theorem about the GNN with strong assumption on the activation function, namely when the activation function and the uplifting matrix commute can commute for all the features. And that is only verified for now for the activation function being the adjacency. That's your SCC network. But for the GCN, we have a nonlinearity with ReLU. So this means that it breaks an assumption. So that's why the benefits of our method are more evident, because we cannot bound it like the training of the GNN. And the weighted version is like very similar to the classical normalization, but just you put more weights on the self loop. So and you put more weights if the cluster of the coarsening is heavier at this node. So that's why it's a bit better than the classical normalization, and it is more interpretable for that case. So that's why it maybe sometimes it has better results.
I see. So does he like give us some empirical insights, like when we do not have the nice guarantee of the activation function in SGC, what kind of coarsening method we could potentially use? Does that give us some insight about it?
Yeah, in fact, the method I use is more a post-processing after your coarsening. You can use any coarsening algorithm, and any coarsening algorithm would give you a matrix Q and a matrix Q plus and a coarsen graph GC. So you can, after, when you decide to train GNN on your coarsen matrix, you can use different choice of propagation matrix, like the same normalization or version. So I would say if you go with SGC, you should definitely try our propagation matrix. And otherwise, I think you should try both our matrix and the weighted version, which is kind of smarter choice rather than the same normalization.
All right, thanks for the answer. I think we do have one question from the audience. So the question is, what are the limits of that propagation function?
What do you mean by the limits more particularly? Like asymptotically, like, or the main drawbacks of the method? Because I would say okay, by the drawback, obviously I would say the strong assumption of on the activation function is one of the biggest limits. We also making another assumption that the features lives in the low frequency of the graph. So that is, but it's more an assumption that we make classically for graph coarsening. So that means it would work more on homophilous graphs than on a heterophilous graph, because if you merge two nodes in the same supernodes but they have different labels, you will have a lot of difficulty to distinguish it. So we make another assumption about the features living in the low frequency of the graph, and then on the low frequencies of the Laplacian, and then on the preserved space. So this is another strong assumption. But as we used spectral guarantees, it is quite classical. I hope I answered your question.
Yes, I think. Yeah, so I guess we can dismiss this question. All right, so if there are no more questions coming up at this point, I guess we will just conclude our presentation for this paper here. And thanks so much again, Etna, for your presentation. And again, if the audience have more questions coming up, you can also feel free to post it in our Slack channel as well. And all right, so I guess we will proceed to our next speaker. All right, so our last presentation today is going to be given by Mikhail Mironov, who is currently a researcher at Yandex. So I think the title for the presentation today would be Revisiting Graph Homophily Measures, has been written here in the slides. Cool. So Mikhail, very nice to meet you. And whenever you're ready.
Nice to meet you too. Can you hear me?
Yes, I can hear you.
Good. And can you see my slides?
Yes.
Yeah, good. Perfect. Okay, so my name is Mikhail Mironov. This is a work with Lyudmila Prokhorenkova, which is named Revisiting Graph Homophily Measures. And yes, we both work in Yandex Research. So the homophily of a graph is the property of the graph that if its nodes are divided in some classes, then if nodes of the same class tend to be connected, then we say that the graph is homophilic. If nodes of the opposite classes of different classes, not coinciding, tend to be connected, then we say that the graph is heterophilic. So the question is how to formally define this property and how to measure it. One important comment here is that measuring homophily is not the same as measuring GNN performance. It's kind of a common knowledge that for homophilic graphs, GNNs tend to work better. But actually, if, let's say, I take fully heterophilic graph with only two classes, like here on the slide, clearly any GNN will work good on it. So it will be able to guess labels. And there is some other evidence that for very heterophilic graphs, GNNs also work well. Another argument about it is that homophily was discussed and was the property long before GNNs ever become a thing. So when we're talking about homophily, we don't want to just predict GNN performance. Basically, what we want is to capture our intuition about which graphs are more homophilic. So if I see two graphs and I think that this graph is more homophilic, I expect this measure to give the same answer, that like this graph is more homophilic. So we'll do it in the following way, like we'll approach this question. We will see previously used homophily measures. We will discuss some of their properties, and based on this, we will formulate like what properties we actually want from good homophily measure. And as if we conclude that all previous measures doesn't have at least one of these properties, and as that we provide the measure which has all of these properties. So let's see previous homophily measures. Here there are a lot of like notation, and like clearly it's hard to understand it from like the scratch. Let me just describe in words what measures we have. Like it's here on the right, there are like 4 measures. First one is H homophily. Basically, so let's say I call an H homophilic if it's connected to nodes of the same class. So I take the graph, I calculate the number of all homophilic edges and divide it by the total number of edges. It's like the simplest measure possible, and it's called H homophily. Second measure is a bit different. Here I calculate, like for each node, I calculate the number of neighbors of the same class and divide it by the degree of this node. In this case, I can say this is like the measure how homophilic this particular node is. And after that, I average it over all nodes. And it's like, I denote it by, I name it by node homophily. Next one is a bit complicated. Let me just like give a sketch of it. Basically, I take all nodes of the same class, I calculate number of its neighbors of the same class, and divide by the total degree of all nodes of this class. And this is kind of a homophily of the class. And after that, I do some other calculations with it and average it. Last one is adjusted homophily, and it's an interesting one. So like this part on the right, which is di divided by 2 times number of edges. So how we can think about it, it's di is the total degree of a class, like the sum of all degrees of the class, and 2 times number of edges is clearly the total degree of like all graph. And so this is kind of the fraction of degree of corresponding to my class. So if I would draw the edges completely randomly, then I would expect the number of homophilic edges inside this particular class, like the fraction of these edges, to be like this di divided by 2e squared. So in numerator, the right part basically is kind of expected number of homophilic edges. Like, so I see the h, so it's like the real observed number of homophilic edges. I subtract the like expected number of homophilic edges, and after that I do some normalization by denominator. So it's like the idea of adjusted homophily measure. Now let's see some properties. We'll see them for H homophily, and based on it, we will formulate like the properties which we really want from homophily measure. So H homophily is just a fraction of homophilic edges in the graph. So what's good about this measure? First of all, if all edges are homophilic, then I get the fixed number 1. So for any graph, if all edges in the graph are homophilic, I get this like the same number, like the good upper bound, which is like 1. The same is for all heterophilic graphs. So like if all edges are heterophilic, I get 0. Like no matter what graph is, if all edges are heterophilic, 0. Perfect. The last one is kind of monotonicity, that like if I have a graph and I add a homophilic edge, then H homophily increases. Or if I have a graph and I delete heterophilic edge, there H homophily increases. Sorry. So that's kind of like good properties which we want from like homophily measure. Now let's see what's the downside. Consider 3 graphs. Like all of them are a Joly model. So basically, I have a bunch of nodes, and for each 2 nodes, the probability of an edge is like, I don't know, 1 divided by 3 or whatever, like some constant probability. So like the edges are completely independent from labels. So suppose we have only 2 classes, and balance of classes is like 50 nodes in the first class, 50 nodes in the second class. So on average, I'll have like half of the edges will be homophilic. So H homophily will be 0.5. But if I have the same like Joly model, I have graph with 2 classes, and the balance of the class is 90 to 10. And I again like draw this edges randomly. The average expected H homophily is 0.82. If I have 5 classes, like uniform and like 20 nodes in every class, and I draw edges randomly, then expected H homophily will be 0.20. But it's clear that like from like intuitive perspective, all of these graphs should have like the same kind of neutral homophily, because like in all of these graphs, the structure of the graph itself has nothing to do with labels. So it would be reasonable to expect to have like the same number in all of these like 3 cases. So this is kind of a drawback of H homophily. It basically says that if I have graphs with different light balances or different number of classes, then H homophily is not reliable to compare such datasets, like which of them is more homophilic or heterophilic. So let's see what properties we have based on these examples. First 3 is like exactly what we mentioned before. So if all edges are homophilic, we want to have some upper bound, R max. If all edges are heterophilic, we want to have some lower bound, R min. And we want some monotonicity, which says that like addition of homophilic edges or removing heterophilic edges must increase H homophily. The next property is like the key property, which exactly the property which H homophily lacks. It's like constant baseline. So how we formulate it? So we want to say that like if a structure for graph is independent from labels, then we have some constant value. So we do it in the following way. We fix all node degrees and all class labels. After that, we kind of cut all edges. So like now every node has like not edges, but like kind of half of edges like sticking from it. And after that, we redraw edges randomly. So we preserve degrees and preserve labels, but all edges are drawn randomly. In this case, we expect to have some fixed R-based value. So we want our measure for every graph like made this way to have expected value R-based. Okay, now there are like 2 other minor properties, but like let me mention them just to like mention. One of them is that if I formally add one more class, which is not present in the graph, so there's no node of this class, I just formally increase number of classes by 1, then homophily measure shouldn't change. And the second one is that if I rename or reorder classes, then homophily measure shouldn't change. Most of these properties were mentioned in like were formulated by Platonov et al., including this like crucial constant baseline property. Now let's see like what properties these measures have. First of all, first 3 measures, H homophily, not homophily, and class homophily doesn't have constant baseline. So basically, they're not reliable for comparing datasets with like different class balances. Next measure, it's adjusted homophily, which was formulated by Platonov et al., and it's incorporated in itself constant baseline. Basically, it's like what I described before, that like numerator will be 0 if we like draw edges randomly. Then like on the left, it's like a kind of observed number of homophilic edges. On the right, it's expected number of homophilic edges, and so it has constant baseline. But unfortunately, this measure doesn't have minimal agreement, and it doesn't have monotonicity for some lower value of adjusted homophily. And our main contribution is that we formulated a new measure, unbiased homophily, which has all of these properties. So let's see. Basically, we will just see this formula for nearly the rest of the talk and just think why it really satisfies the properties which we described. We denote by CII the fraction of homophilic edges inside class I, and by Cij half of this heterophilic edges between classes I and J. Now introduce the formula below. First of all, it's dependent on some coefficient alpha, but let's for now ignore the second term. So it's not really important, it's more technical. And the crucial term is the first one, which is right now in black. And let's see what it means and like why it makes sense at all. So first of all, suppose we have no heterophilic edges. Then all Cij is 0. In this case, numerator and denominator basically is the same value. So we get 1. And like the first term is equal to 1, so we have maximal agreement, perfect. The same for minimal agreement. Suppose we have no heterophilic edges, no homophilic edges, sorry. So CII is equal to 0 and all edges are heterophilic. In this case, all these square roots are zeros, and the numerator is basically the negative of denominator, and we get -1. So we get minimal agreement. I'll say nothing about monotonicity, but you can like it can be proven that like it has monotonicity in most cases, whatever. Now let's see the most important part is like why this has constant baseline. It's like the main property which like previous measures lacks, excluding adjusted homophily. So suppose we are in this setting when we cut all edges and redraw them randomly. Suppose like we are in this setting and we know the like the fraction of degree of class I and the fraction of degree of class J. So suppose I know it now, what can I say about coefficients CII and Cij? So like I know like the fraction of the fraction of like this half ages, which correspond to the first class and to the second class, like what can I say about CII and CIJ? First of all, like CII will be just the product of like fraction di divided by 2e like squared. So it's just the probability that I pick like the first one from this fraction, the second from the same fraction. For CIJ, we have the same, and for CIJ, it's like half of the heterophilic edges. We'll have this formula di times dj divided by like this 2e times 2e. So, sorry. Oh, okay. Okay, so the conclusion here is that based on these formulas, we can see that if we are in this random redrawing edges situation, then we expect this square root of CI CIJ to be equal to CIJ. So basically, this proves that the expected value of numerator is 0, which is good. Like this basically proves the constant baseline. So yes. So another kind of intuition how to interpret it is that this, like, if I know how many homophilic edges I have, so I know CII and CJJ, then I can expect the number of heterophilic edges to be square root of CII CJJ. And so this square root is kind of expectation, and CIJ is like what I really observed. And I take the difference. And like if this difference is 0, then I'm exactly in this random situation, which is constant baseline. And yeah, if it's above, then it's more homophilic. If it's below, it's more heterophilic. Okay. So now, yeah, now let's see what the second term is about and like why we at all need the second term. The problem with the first term is the following. So suppose only one C, like the CII is more than 0. So let's say C11 is bigger than 0, and every other like C22, etc. are 0. So like we have only heterophilic edges only in one class, basically. Then you see that all square roots will be zeros. And in this case, like the first term will be just -1 because like the numerator will be just minus the denominator. And that's clearly not what we want. Like, I mean, it violates like the minimal agreement and it violates like monotonicity because like now if let's say I increase C11 a bit, the first term will still be -1. And so the second term kind of fixes this. So like in this special case, when like only one CII is bigger than 0, like the second term fixes it. I won't dig deeper, but here what you can note also is that the second term can be arbitrarily small, basically. We multiply it by some alpha, where alpha can be any number, basically. Okay. So this is our formula, which like has like all desirable properties for all alpha bigger than 0. But in practice, since alpha can be arbitrarily small, we recommend just to drop it and use just the first term because like it's the most crucial and it has nearly all properties. Like so, excluding that it violates monotonicity and minimal agreement in this rare special case. Other than that, like this first term is perfect, and like we recommend to use it. Yeah. By the way, it's like kind of we give an example of property which satisfy all the. We give an example of measure which satisfies all properties, but we do not say that it's like unique measure. Maybe like clearly there are like other measures which also satisfy this property. Okay. So it's like, again, the review table with properties and measures. Here you can see that unbiased homophily with alpha bigger than 0 has like all properties. And when we drop the second term, we just have some like small star with minimal agreement and with monotonicity. Okay, I think this is nearly it. So in our paper, we also include some examples of desirable and undesirable behavior of homophily measures. And we compare them for different synthetic and real datasets. Also, we try to solve the same problem for directed graphs. Oh, well, by the way, like this thing also can be applied to weighted graphs. So like it will work the same way. But like for directed graphs, unfortunately, properties themselves contradict each other. So like it can be proven that if we directly reformulate these properties for directed case, then there will be a contradiction. So we need some other properties. I think that's it. We also will have a poster session tomorrow, so come there and like ask us some questions. We'll be glad to hear them. Thank you. That's it.
All
All right, great. So thanks so much for your talk. I think we still have a little, we're actually running behind schedule. Actually, the post has already begun, but we still have, because we started late, we still have a few minutes. I guess we can still take 1 or 2 questions if there's any. Yeah, as usual, I guess I'll still give people a little bit time to type in questions. And I guess I will also just utilize this small gap, if there is any question, to ask my question. So I think you started by motivating about the relationship between homophily measures and the performance of GNNs. So I guess my question will be later on, because you have proposed your own homophily measure. Is there any insights that we can talk about between your homophily measure and GNN performance?
Oh, we haven't measured it yet, but in general, like I tried to actually distance from this GNN performance because, again, as I said, like GNN works well for fully homophilic graphs, but for fully heterophilic graphs, they also like have like surprisingly good performance. So they like the drop in the performance usually is in the between. Then there's like neutral homophily. Yes,
I see. And also, I guess the other question that I had was like, do you have some of the like real statistics that that you obtain after running your measure on real world data sets, like some of the very popular data benchmarks that we use?
It's like not statistic. Basically, we have values of like different measures for different real benchmarks. Yes. And we can see that sometimes, like, let's say if let's say H homophily says that like this benchmark is more homophilic than like one benchmark is more homophilic than another one, and we can see that it happens just before there is some class imbalance or something. We can see that our measure works better. That like it compares them in the way which we expect intuitively, that like we formulate with our properties.
Yeah, I mean, it would be nice if we have some kind of, I guess, counterintuitive examples of things that we think should be homophilic, but at your measure it's not, and things like that would be very nice to show if there's any.
Yes, but like it would be not nice in some way because like it will say that this measure actually bad. Like it means that you haven't counted in something. It will mean that like our intuition wasn't captured by the formula. Like,
yeah, true.
The idea was to so. But like if you find such examples, it will be like good. It will be like step forward. Maybe you'll find some other properties.
Yes. So I think we do not have more questions coming up. Yes. So if there's anyone wanted to have more discussion, please feel free to post questions, comments in our Slack channel. And with that, I think we will just finish today's oral presentation. Thanks again very much for Mikhail's talk. And our poster session is right now underway in our Gather town hall, I think. So I would encourage those of you who are interested to move there. Thanks very much again for everyone for coming.